And there we go. All right. So just want to clarify one more time if people could hear me, because I'm still hearing some wonky stuff on my headphones.
Yeah,
Yep.
you sound good to me here.
Cool. Awesome. Super cool. All right. So this is the review session for CS 365 Part 2, Electric Boogaloo. And basically we're just gonna the last one was kind of like super honed in on like detail. I was thinking we could cover like more broad topics and just like cover each thing instead of like honing in on one specific question for each topic in the class. And and that's kind of the goal. So I had like an outline, but it seems like a lot of people don't want breaks, which is cool. That's fine. And then also definitely proofs. Everybody wants to focus on proofs, which is cool. And then one person wanted to focus on the material and references, so we could just cover that really quick. And then we'll mostly move on to some of the homework questions and quiz questions. And I wanted to be prepared, so I did write some stuff down, and I have like 3 from each homework session. And I have the virtual book, so I'll just share my screen, and we could go over some of those. So starting with the well, first of all, does that sound cool with you guys? That whole setup?
Yeah, absolutely.
Cool. Okay, so starting with the material. So this is an open book exam, and I went to the professor's office hours yesterday when we had the quiz, and I wanted to ask him if we could have the calculator, and he said yes, graphing calculator as well, that's allowed. So whatever calculator you have should be fine. Make sure it's charged. Bring that with you. And then for the actual material of like what you want, it's open book, so you could bring your book. But I mean, it'd be kind of like hard to flip through all of the book stuff. So I recommend instead like either like putting, you could print this out, or you could get like little sticky notes and like put it on specific pages. Because you could have the book with you, and you could have your notes with you as well. But I've always found like flipping through the notes during the exam, I don't want to like waste time, And so
Right.
I made this little paper, and you guys could always add on to it. I put a Word doc, I think, in Discord in the resources, and it just kind of goes over like the tables of like it's broken down into each like homework section basically of like what the converse and little definitions and tables and like logical equivalence, um, negation, because that was definitely that was even a quiz question, I think, about like negating quantifiers, and how that kind of like levels down. And we'll go into that in one of the homework questions. But of course, we'll also focus on proofs because you guys are here for proofs mostly. But I mean, this one hurt as well because I think that was the lowest average quiz. I also did not do well on that quiz. So that's always good to go over that because I think, he might hammer that in since he noticed that the majority of the class did kind of iffy on that. I have all the proof definitions of direct and indirect and, straight from the book. Technically, I don't know if that's illegal, but I mean, hopefully it's not because it's just, you can see my screen, right?
Yeah.
Okay, cool. But I mean, I bought the book, the physical book, so I'm just thinking like, hey, you guys also bought the book, hopefully, so we're all good. And yeah, just feel free to grab this and download it. I also have some examples because Aiden, I think, so someone from the last Discord session, study session, was talking about like, hey, we should go over this thing, and this was in the book, and he also went over this exact same thing in slides. So I don't think it would hurt to have the answers and like step by step on how to do that with you, because I mean, if it's in all 3, then it's probably going to be on the exam, and might as well reduce the thinking power by keeping that out of the way. Anyway, I'm just doing like a soft kind of scroll through to show you what's going on, but you can always feel free to check this out on your own time as well. And if you update it, feel free to like, I would say like share it on Discord so we could all kind of have an updated version too. And yeah, we'll go over like a little bit of sets, but once again, mostly proof stuff. And yeah, that's kind of the whole thing there. So I'm going to close that out. And what else? What
Thanks
do
for
you
putting
guys?
that together.
Yeah, no problem. No problem.
This is actually way more in depth than I thought it was.
Yeah, I just wanted to get all the tables and stuff because I mostly it's just tables. I mean, it says 22 pages, but it's mostly just like the
Right.
yeah, all that stuff because I don't want to memorize,
Yeah.
all that stuff or indirect proofs and that whole thing. But yeah, no problem, no problem. We're all in this together and all that stuff. And if you guys have any recommendations for what people should bring, go ahead and give your 2 cents because I think that'll be cool too.
And I just wanted to make sure this isn't like it's now just a Zoom thing. It's not Proctorio, right?
Yes, it is just that he said that it's just like the quizzes. So basically, you're
okay.
going to hop into Zoom, turn your camera on, and then he's just going to give us a passcode to hop
Right.
in there, which is also why
Okay.
it's available right now. If you check it out on Canvas, it says available until
Gotcha.
yeah, but you can't really hop into it because you don't have the code.
Right.
Which stresses me out a little bit. It stresses me out that the button's there, but it's good to know that I can't like accidentally like take the quiz right now or take the midterm.
Yeah.
Is it just like the quiz where it's, quote unquote cameras on? Like, does he care or?
I think he will be more strict on this.
Yeah, I'd expect him to.
Yeah, I'm not 100%. I don't want to speak for the professor, but I would say if you have a camera, well, my girlfriend does. She does not have a camera on her laptop. So what she does is she has two. You could log into your Zoom account on your phone, and you could have that like angling over your computer or something, or like set up against the wall. And she does that for her quizzes. So you can always do that too.
Okay.
And if you don't have a phone or a camera, I don't know. Telepathy. I'm not sure, but hopefully, your phone camera will work. Or you could email him. He's a nice guy. I've been to every single office hours except for one, and he's pretty chill. So if you email him and let him know, like, hey, I don't have a camera, yeah, he'll hook you up for sure. He'll give you something that will be good enough. He'll probably just be like, you don't need it or something. He seems pretty lenient about that stuff. And yeah. Anything else do you guys recommend for the midterm, like bringing or like material wise to have on you?
Not really. I think this like sheet that you set up pretty much covered basically everything.
Yeah, gotcha.
Or just like the basic stuff that we have to memorize.
Yeah, for sure. But if you guys ever have anything, just let me know, and it'll be on record. Also, I don't know if this is important to know. Like, if you're thinking like hopping in and kind of like how you want to break up taking the exam. Like, I don't know if that's kind of like nitty picky at this. That's not how you say it. How do you say it? Nitpicky. Nitpicky. Yeah, that's it. Nitpicky, but I'm still gonna probably go into it. Oh, also it says if you actually click on it, I did not notice that. If you click on it, this is also helpful. It says turn your camera on. So there's like a little list of instructions.
Right. Yeah, it does.
Yeah. And then you are gonna want your phone on you because it says for file upload. Well, unless you type it, I'm gonna write mine. But if some people are faster at the typing, that works too. And yeah, no communicating, basic stuff, textbook, lecture notes. So I would keep the lecture notes up too because there's a lot of examples in those. But I wouldn't like fill your tab up with them. I would pick out which ones, maybe screenshot some favorites or whatever. And then like there's only 12 questions on the exam, so I don't know, there might be like half free response, half multiple choice or whatever.
Yeah, I do really wonder how many like proofs he's going to be having us do.
Yeah,
because those can take a while if you
yeah,
don't know like immediately where to go with them.
yeah. So I would probably what do you think? You should like do the multiple choice and then the proofs, do you think that'd be a good like
Probably.
strategy? Yeah, that's what I would do. It's like if you see a proof, avoid it, and then get to the ones, because they're all probably going to be the same amount of points. And we all kind of struggle with proofs, at least according to the poll. So I would focus on the stuff you do know first and then hit the proofs. Anyway, hope that helps. Whoever asked that question, it was anonymous, so I have no idea. But yeah, and then I was thinking we'll go into the homework section. Do you guys want to start with all you guys talked about wanting to do proofs? So do you guys want to start with the proof homework, which was homework 5 and 4-ish, or do you want? Oh, sorry, homework 4 and 3. I started, or do you want to like start like bottom up, like 1, 2, 3, or do you just want to start with proofs and then go out from there?
I'm okay with just going down the line just to get some review of the stuff that we just don't have as much of a struggle with, and then getting into the meat of it.
For sure. What about
that works for everybody else?
Gotcha.
I agree with that.
Do you agree? Okay, cool. Everyone agreed?
Yep,
Cool.
sounds good to me.
Cool.
Yeah, sorry I'm late. I forgot this was starting. Did we already go over the quiz questions?
No, not yet. We were just covering like what you should do, like what you should bring to the exam, and like what the exam is going to cover, and like how many questions, and you could bring a calculator, graphing calculator. Yeah. You didn't miss much, but it's good to see you, Adam.
Okay. Yeah. Graphing, actually, just as an aside, not to toot my own horn or anything, but I completely forgot. I studied the wrong section for the quiz yesterday, but I still did pretty well, because for the onto and one-to-one questions, like is this an onto or one-to-one, you can graph that and reason through the graph. So if it's one-to-one, it has to pass the horizontal line test. If you graph the function, it can only bisect the horizontal line once. If it's something like a parabola where it would cut through twice, that's not one-to-one. And then onto has to cover the entire codomain. Everything in the codomain has to be accessed from the original function. So if there's something in the codomain that is not covered, for example, you only have positive numbers on the y-axis, then half that codomain of the y-axis is not covered. That's not onto. So just as an example of how you can use the graphs to help reason through some of these questions, bring back a little bit of, I guess it would be pre-calculus.
Awesome. Thank you, Adam. That's super
thanks
cool.
for bringing that up. I completely forgot that. Yeah, you can use graphs to reason.
Yeah. If you just, and it doesn't have to be super exact either. You just need to kind of be able to do the general shape of it. And then say, X is my domain, Y is my codomain, and go from there.
Awesome. Thank you.
Yeah, the horizontal line test has absolutely saved me on several of those questions.
Give me 1 sec to find, since you guys want to start bottom up, give me 1 sec to actually find the virtual page of the homework. Okay. So I was thinking of doing 3. I don't know if I'm sharing the right screen. I hope I am. Do you guys see like the exercises?
The textbook?
Yeah, we see it.
Okay, cool. So I was thinking of doing 3 per homework, 3 questions, unless they were like super like specific, like the ones you guys want to work on. We could do more than 3, obviously. But for like the ones that you guys feel pretty comfortable with, do you think 3 out of each homework would be cool?
Yeah.
Cool. If not, if you have like an extra. Cool.
I'd say if we get into it and we recognize that we need to cover something else more, then we could just continue to pull problems.
Yeah, sounds good.
But are we just starting with section, what is this, 1.1?
Yeah, 1.1. So
Okay,
I'm just doing each homework problem. Well, not each homework problem, but each homework, 1, 2, 3.
Problems from each homework.
Yeah, exactly. Thank you. Whoops. Sorry. Okay, so the first one I thought was super important was homework 117. So let's just go to that. Not waste any time. And so obviously we won't do all of these, but I think some of them are pretty important. So this is the grizzly bears and then the hiking, and then you're basically turning a sentence into propositional logic. So we could do like, definitely I want to do E, because E was a big one.
Yeah.
And then maybe like C and A or something. So we'll start with A, and I don't know how I'm exactly gonna like write on this, but also you guys could feel free to annotate too. And enable annotation for others. There we go. So I would say for the first one, berries are ripe along the trail, but, and you want to say that but is a keyword, which basically is and. So I would put a little and sign there, which is I believe it's called a conjunction. And so grizzly bears have not been seen in the area. Not is a keyword. And so then going over to the pen tool, I would say, hey, berries is R, and sorry for the bad handwriting. Grizzly bears have not been seen. Grizzly bears is P, so that P. And there you go. Answer A. And then for C, if berries are ripe along the trail, so if we're already seeing a keyword, and then we'll just say, hey, berries, and we'll go R, and we know if means conditional. And then this comma, hiking is safe if and only if. So that comma basically means then. So we could think of this as parentheses in here. Hiking is safe. Okay, we know that's Q. If and only if, that's a keyword, which means biconditional. Again, let me know if you can't see this too well or something. So if and only if grizzly bears have not been seen in the area. So again, the keyword not, if and only if, and we have no grizzly bears, but we do have, it is safe to hike. And there we go. That would be C.
And so the main two things for like the biconditional are like if and only if, and then necessary and sufficient.
Yeah.
Is that the two?
Yeah, absolutely. I would say. Actually, let me. Let's see.
Necessary means it's part of the recipe, it's part of the list of things you need. Sufficient means it's enough to satisfy the condition. So if it's necessary and sufficient, you have everything and you have enough to satisfy it. As a spoiler for E, if it's necessary but not sufficient, that means one of those propositions is needed to satisfy the condition, but you don't have enough to make the whole thing be true, I think.
I totally agree with that. Yeah, and it's also on page 10 if you have your actual book on you. I don't want to scroll up and mess this up, but it says just exactly what Adam was saying. Necessary and sufficient biconditional, and then also the weird like IFF, like P if Q, but it's like IFF. That's also a thing. I don't
Right,
think
that's the
about
if
that.
and only if.
Yeah, but yeah, those are the two I would look out for biconditional, and then E. Right, E. For hiking, be safe along the trail. So that's obviously Q. We're talking about Q. Well, let me move it over here. Q. It is necessary, but not sufficient. So we're definitely going to have a not somewhere. I'm just going to put a not there just to remember that. That berries not be ripe along the trail. So what is that? That's not R. And for grizzly bears, not to have been seen in the area. So we see and. So this is and. Grizzly bears, which is P. something like that. So for hiking, it is necessary but not sufficient. So again, we see but, which is a key word for and. So I'm gonna put that there. So we have one that's necessary, but, which is our and, not, and then sufficient. So I would say what Adam was saying is that it is necessary, means that Q would be, I believe, the end result because it's necessary. Is that correct, Adam? I might be off on that. So
Q would be implying in this case.
I was scanning through the book trying to find something. I wasn't really paying attention.
No, you're good.
Need a minute to think about it.
Gotcha. What are you saying, Eric?
Are you saying that like, were you asking if Q is basically being implied or doing the implying?
I think it would be like this. I think
Right.
because they're
Yes.
saying necessary is the other thing. It is necessary that this is happening. So this is the necessary part.
Yeah.
Yes.
Necessary is an implication.
Gotcha.
That's on
Is it
page
implication?
7.
Gotcha. So is it the other way around?
No, you got it.
Okay. Just like I don't have the answers for these guys, but I chose the tough
Well, I
ones.
mean, I think we did this homework, didn't we?
No, we did. Yeah, these are the ones from the homework. But if you have,
Okay.
like, if you flip back to it, you guys could let me know if this is correct. 'Cause I
Yeah,
don't
let
know the
me-
sky anybody.
Let me look at what I have there. 17. Yeah. Oh, yeah. He's the crazy one. Okay.
Yeah, he's the crazy one, which is why I thought it was a good one to choose.
Yeah. You definitely have. So that's Q implies. What is it that follows? Is that N?
Oh, I'm just saying N is, let's say N is this guy for right now.
Oh, okay.
Yeah.
So that's not R and not P.
So
Right.
Yeah,
And then-
that's correct. And then
Cool.
and not.
then this would be the other way because sufficient.
But that's Q.
Sorry. Yeah.
But yes.
I even wrote it like exactly. Yep. Absolutely. Thank you, Eric. Yeah. Q. Sorry.
What I have instead, it's mostly right, but there's no implies Q.
Well, I'm just going off the back of the book ones.
Oh, is that what it has in the back? Oh, okay.
Yeah.
Is that what it has, Eric?
Yeah. I'm pretty sure. Let me take another look, but I'm pretty sure that that's exactly what's in the back.
that's right.
Yeah. If one of you guys could keep that on file, that'd be cool. Just because I don't want to keep flipping through the.
Yeah, no worries. I'll get that
Yeah.
open.
Cool. Thank you. But yeah, that is kind of how you want to think about this problem. Is that necessary is at the end because if necessary is true in a Q statement, if Q is true, then the whole thing is true. So that's basically your necessary, and then
Yep.
sufficient. It's the other way around. So you get
That
Yeah.
is
this
the answer in the
sufficient.
back.
Cool.
Yeah.
Perfect. All right. So is that cool with everybody? And we can move on to
And-
the.
Like
Yeah.
Adam said, on page 7, it does a good job of kind of explaining the implications because it says that like a necessary condition for P is Q, which inherently means Q follows from P. So that's where we're getting that original, like Q implies the negated R and negated P.
Let me try. I don't want to necessarily commit to it because I do have some things to get to and I don't know if I'll be able to finish it. But I would like to try to make a cheat sheet for this class that summarizes stuff.
There's one in the resources you could add on to. We talked about it in the
Yeah,
beginning.
Gabe
the
posted one that
resource.
that had a bunch of stuff in it already.
Which one?
The newest one.
Oh, the midterm?
Right.
Yeah. And then
Okay.
I'll move on to the next question, if that's cool with you guys. Unless somebody's still confused about E, if I didn't explain that too well, or if
Oh, wow. Okay. Did you make this?
I did.
Oh, wow. That's pretty good.
Thank you. I tried hard. I tried really hard.
Had this really
Um,
official looking front page and everything.
Yeah. Fancy.
All right. Well, I guess that looks pretty comprehensive.
Yeah, feel free to add on to it, or if you ever need to. But
No, this is kind of what I was envisioning. Just, yeah, that's pretty good.
Cool. Okay. So I'm gonna take that. If somebody is still confused about E for 17, let me know. But I'm gonna move on to the next one. And the second question in homework 1 was 41 that I thought was kind of rough and tough. And construct a truth table. That might actually take some time. Basically,
Was
I'm
it the one
gonna
that took like an entire page.
yeah,
Yeah,
I'm gonna
Yeah, it is.
I was just going to explain like what the truth table for biconditional is, and then from there, I'm hoping people could kind of follow through with that because I know that we want to focus on proofs today. And so for biconditional, if and only if, so that means basically either they are both. Let me actually write this out first. Sorry, trying to get ahead of myself here. I don't even have it on the board. There we go. So biconditional is basically if and only if. So that means they both have to be true, otherwise they're false. And I believe they can both be false as well. And there you go.
Yep.
So it's the opposite of an exclusive or, which is where only these guys are true.
Right.
So just be wary of that. And yeah, we'll move on to the next one. So basically, for this question, you would do this. You would get not Q down first. Wait, sorry. You would get for 41. You would get you would write all that down that I basically just wrote. You do the same for R and S, just basically change the letters, and then do the same with the two statements together.
Right.
Yeah. And so I'll move on.
I hope we get a truth table question because they're not generally hard. It just takes a lot of writing.
True. Very true. I agree. And then the last question for homework 1 that I wanted to go over was 13. And 13. Right. So these are like basic kind of, well, not basic. I don't want to say basic, but they are propositional stuff. This was also on the quiz, I believe. Some of these, and we'll just cover like 2. So the last 2 look pretty tricky, like this one and this one. And it has another necessary and sufficient if people were still kind of confused about the 17E. So I think that's good to go over. So either it is below freezing. Okay, well, it is below freezing. Cool. So we know that's going to be P. And we have either, so we know that probably an if statement's going to go here. Basically the same thing. So either, oh wait, no, I'm sorry. That's an or. Either it is below freezing or it is snowing. So I would say or it is snowing. But, so I put that like that. But, which is and, it is not snowing if it is below freezing. And I did not make enough room for this. Here, I'm going to bring this over here. We have Q and P, which is the same thing. And we're going to say, but if it is snowing, if it is not snowing, excuse me, if it is not snowing, then it is not snowing if it is.
Yeah, just put it,
I think you
arrange
got
it the
that
other way.
backwards.
So it just says, if it is below freezing, it is
Right.
not, then it is not snowing.
Thank you
Yeah.
very much. I had
Yeah.
a little strong there. Okay, other way around. Sorry, everybody.
That's all right.
So P and that would be not Q.
Yep.
Yeah.
Very cool. Okay. Yep.
Now-
So
I just want to interject one thing. First of all, you wrote A and P, or A and
sorry, Q.
or Q and. I think
Yeah.
it's
Q or.
or. But
You're
I would
absolutely
actually,
right.
I would argue that the way it's phrased makes it sound like it's supposed to be an exclusive or, that only one condition can exist. But that's not really one that we covered a lot in this class.
Right.
So, but the way it's phrased makes it sound like exclusive or.
So
yeah, that thing
either
confused me with it too. It made it look like exclusive or. So, I mean, I just put or for that one, but I wasn't sure. Yeah.
yeah,
I would assume
feel
that he's not going to throw anything like that at us on the midterm where we have to determine if it's exclusive or inclusive just in like these kind of problems. Like he might ask us like, like the basic quiz question of like, is each of these an XOR or is it just a normal OR?
Yeah.
But I don't think in terms of prepositional logic that we're going to have to actually decide.
Probably not.
Gotcha. And you got to be careful of where that if is because it might be, this one was the first.
Mhm.
Right.
Cool. So moving on with that. Next one was G, and that it is below freezing is necessary and sufficient. So that's our keyword of biconditional for it to be snowing. So we have basically Q biconditional, or you could say the other way, P. You could also say P biconditional Q, and we do the same thing. Well, I know they're the same thing. So either or. Does that sound good to you guys?
Yep.
Yeah.
Cool. Awesome. So moving on to the next homework. And sorry for that confusion there, but I'm glad I learned something. Always good to fix those mistakes. So homework 2, 1.3.
That was the one with all the truth tables.
Yes, that was all the truth tables. 1.3.
So many truth tables.
Let's see. Number 11 was the one I have for this one. So show that these conditional statements is a tautology. So we're not obviously going to go over each and every one of these, but there's 2 ways to do this. This one says using truth tables. You can also do it on, gotta scroll up for a second.
It's 15.
Yes,
This
you
was
can also
applying
do it.
the logical operators as well.
Yes.
Mhm.
And so you could do it either way. I actually have it combined here. So in here I say 11 and 15, D and E. So for this one, we have D and E. And obviously we could go through writing the truth table, which might take a little bit of time, and I am obviously not masterful at this pen.
Yeah.
Yeah.
I would just suggest, because the truth tables can be rather tedious,
Yes.
maybe just go over how to convert the statement into the columns and not actually fill in all the values, because we just trust that people can figure that part out.
Right. Because I mean, once you're able to break it up into each specific thing, it's not too hard to put in the values and then just solve.
Mhm.
Sure.
Just a
So
suggestion. It
you're
might be a better
saying,
use of our time.
like break up each one? Is what you're saying?
Yeah, so if you have a complex statement that's got all these implications and negations and parentheses, how do you break that up into the appropriate columns of a truth table so you know what to add? I feel like that would be something that perhaps some people,
No, yeah, totally.
that's kind of like the main skill, because the rest of it is just
Knowing the truth
filling in
table.
values. Yeah.
Yeah, that's fair. Okay. So for this and, we know that if this only happens if they're both true. So I usually like to break it up by the symbols because I'm kind of a visual dude. So I look at this and I go, okay, so I need to know if they're both true, then we get a true. Otherwise, they're all false. So we got that. We got that all covered. And then for the second one, whenever there's an arrow, I usually just look at the last statement then, and I look at this and I go, okay, P and Q, we know that for conditional statements, we need Q to be true to have a true thing. Well, not always. So we can have this, and that would be true. So if we have P and Q, sorry for this, and we have P implies Q, then we have the true, 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 false. Sorry for the handwriting. Okay, so if they're both false, then we know it's true. And if the Q is true, then we know that's true. If Q is false and P is true, then we know that this is false. And if they're both true, then that's basically this one's my favorite one because this one's like I absolutely know that if they're both true and they're both false. And then I usually have to think about this one, but just think of like the last kind of statement as being, remember, necessary. So if that's false, then it can't happen. And that kind of helps you on other questions where it's necessary or sufficient. And so you could do that. And then you also have your truth table with the and, where it's if they're only both true, then it's true. And basically then you break that up into having this, and I'm just going to carry this guy over just here and just pretend we have the same kind of thing going on. Sorry, this is a little confusing or a little messy. So this is basically the conjunction. This is the implication. Or sorry, this is the conditional. And we're going to give it into our final result of doing it over both of these two guys, of this guy and this guy. And so we know that if they're both true, it's true. So we're thinking it as a conditional of these two previous boxes. If they're both false, then it's still true. And then the last two, well, it's F and F. And so, I just realized the mistake. But I'm still going to write it
You
down.
flipped them backwards,
Yeah,
but they
I
are
did
still
flip
true.
it. I did flip it, yeah. So, well, in this case, in this exact case here, it would be false, but they should be true because, because it's the other way around. Sorry about that, everybody.
That's why it's kind of important just to keep track of each where you're putting it, and because you can make it more work on yourself in the case that like you have those two inverted like they were before.
Yep.
Because otherwise it's just a simple read left to right and you can easily get the next implication. But if you flip them backwards, then you have to keep track of which one is the right side and which one's the left.
And I'm kind of glad I messed that up because then that's a perfect example of how you can mess up on the exam. And so you don't want that. So yeah, this is true, both false. This is true because necessary. And then this is true. So there you go, tautology. Don't do what I did on the exam. Make sure to get all your mistakes out right now. So thank you, Eric, for pointing that out. So yeah, totally for that one. And then we can break that up and we'll just do the logical equivalence thing, which I'm way better at, hopefully. So that's D, and we're talking about P and Q implies P implies Q. So the first super important thing is you want to know that P implies Q is logically equivalent because you're going to use this like a bajillion times to not P, I believe, or Q.
I think it's
Is it and? Is it and? Okay.
Yeah.
Is it? I thought it was or.
Oh, is it?
Well, that's why you want to have
Could be
the
wrong.
table.
Let me check.
Hold on. Yeah, I should.
But once again, that's absolutely why you
It
want
is.
to.
It is. No, it is
It is.
or. You're right.
It is or? Okay,
Yeah.
hooray.
I misremembered it.
No, you're good. You're good. That's why I have mine printed out. I have the thing printed out here of the review thing. And so that's important. And so basically you could break it up and you could say, hey, we'll break this up first and we'll go not P or Q. So that's good. And then we have implies P and Q. And once again, I know you guys want to get the proofs, but just covering this guy first. And then basically you could break this whole thing up into saying, okay, not, think of this as like its own P. Right? You could think of this whole equation as a P and this whole equation as a Q. And so you could say implies, and then you could just keep that normal. Oh, wait. Not implies. Or, I just went over that. Sorry. Or this. Because this is kept normal. This is inverted. You can take this and kind of foil it. But I know some people don't like to think about it as foiling. So you could just think De Morgan's and flipping everything. You could say not P and not Q and not P and Q. I'm saying this specifically because I know it looks bad, so I'm just saying them out loud. And then you can look at that and go, okay, not P and not P. Well, that's not really important. You could basically combine those. I'm just combining these guys and this guy, but really it doesn't matter for the final result. We're mostly focused on this guy, which you should know by domination law. If you don't know, that's fine. Just write it out. You could say 0, 1, 1, 0, or 0, 1. And then think about basically oring them. And you go, hey, there's a 1 there, so 1. There's a 1 there, so 1. So you know this is going to be true. And so you get true, ored, with A and P. And so then basically same thing. You can make another truth table and do the same thing, but you know it's going to be true. And so there we go. Hooray. Everybody's partying and we're all having a great time.
Did we ever go over
Is it true or false? Yes. It's one of them.
That's
Did
all.
we
I
ever
mean,
go over any sort of equivalence with a biconditional statement, like similar to how we have like essentially negating a implication goes to that one specific or? Did we ever go over anything with a biconditional?
no, but we can.
No.
Not in.
I'm just wondering if
hallmarks.
that's a thing, like if there is a specific logical equivalence for a biconditional.
I think you have to show. Well, I don't know. That would definitely be in the little review pamphlet thing if it was in there. Let me check.
Well, you can. It can be split up if you have P and Q as a biconditional with each other. It can be split up as P implies Q and Q implies P.
That is true.
They both imply each other, and that's AND. So that's
Right.
And another way to do it is P implies Q and not P implies not Q. Oh, there it is.
Yes, that's it.
Yes, there's actually a couple ways to break it up.
Yeah, and that's
Okay,
also in the review little paper thing in Discord if you want to check that out too. But yeah, I would definitely have these on hand because I am not memorizing that. But yeah, I would recommend that. So thank you, Adam, for pointing that out because I completely
Yeah,
forgot about
thanks. That helps a lot.
Just to save time, do you guys want to go over one more like that, or do you think that's pretty solid on that? It's up to you guys.
I think this homework is pretty solid.
Okay. Sounds good. I do have one. Oh wait, one, two. I also have one on 29 real quick. I just want to see if that's even. Okay. That's kind of so same thing. You could break it up into a truth table for 29, or you can break it up like by saying, hey, this is not P or R, and this is not Q or R, and then break all that down, and you'll notice that there are two different R's here, and I believe they will combine to somehow be this, basically. And you could break this down, of course, as well. And I think that would all work out.
Yeah, the way I generally go about it is just simplifying it down to basically just the ors and ands. And then
Yeah.
from there, you can generally speaking either just eliminate things by domination or just do something different.
Yeah, for sure.
Like just group them together if they're the same term. So it makes it easier to me to just continue to simplify it rather than breaking out a whole truth table to check.
Gotcha.
Truth table is kind of the bulletproof way, but man, that's so tedious.
Yeah,
Actually, it's
exactly.
not bulletproof. You can make mistakes and get things switched around.
Yes, and if anybody is a little confused on obviously my handwriting, Adam was kind enough to throw the same thing in chat, so you can check that out.
Although
too.
I don't think it'll show up in the recording, but oh well.
that's okay. It will install exclusive privilege, exclusive membership. Let's see. Last one. I'm just joking, by the way. If anyone's watching this and wants to see what Adam wrote, I'm sure you could message him and get it.
If anyone
Homework.
wants to see what he wrote, you should have done the homework.
Yeah, it's just number 29. Just
Yeah.
plus it.
Okay, I have one last one, homework 2, and it's 1.4, number 23.
Yeah, the universal stuff.
Yes, and that stuff is kind of gunky sometimes because that was the quiz that the average was pretty low on.
Oh yeah, is that the one?
That's the one that so many things sound right when you look at them,
Yes,
and then they just turn out to be wrong. You're like, well, all right.
Yeah.
that's not 23. This is 23. Let me mute my phone. Sorry for the noises. That's interesting. Apparently, my girlfriend made oatmeal and it was bad.
Oof.
I don't know how. I think just throw in the microwave? Question mark. What colors do you guys prefer before I keep going? Is this a good color? Or do you prefer like the purple again, or is that too dark?
That's fine.
Yeah, green looks
You can
good.
stick with the
Green
green.
looks good. It's
Is the
bright.
yellow better?
If it's on the black, I think yellow is better, but I think if it's on the white,
Yeah, that's fair.
it works.
Ooh.
Yeah, let's stick
Let's
with the
stick
green.
with green.
Let's stick with green. Okay. So for each statement, find a domain for which the statement is true and a domain for which the statement is false. That is not this
23.
question we're doing. Sorry. Translate in two ways each of the statement into logical expressions using predicates, quantifiers, and all that good stuff. First, let the domain consist of all students. Okay. Domain is the students. That's a D, but looks like a P. And second, domain consists of all people. Okay, so someone in your class speaks Hindi. Okay, so we know that someone in our class, that's going to be a student. All students in our class. In class. Oh, geez. Well, hopefully you can somehow interpret that. Okay, so someone in your class speaks Hindi. So obviously, if we're talking about the first case, I believe that would be everyone. And we're talking about X, we could just say everyone in the class, and we could say H or something to that effect. And we could say H, the function H of X is X speaks Hindi. And once again, apologies for the handwriting. But that's what I would say. And then,
Well,
yeah.
If it's just someone in your class, that's not everyone.
Right.
I'd say someone. Oh, whoops.
Yeah.
Thank you.
So that means it implies.
There exists.
Yeah, English
someone.
isn't precise, but it implies there exists only one,
Yes.
or at least one, I guess.
For some reason, I interpret that as everyone, even though I read it. Okay, everyone in your class is friendly. Obviously, that would be exactly what Adam was saying. A of X is that, and that would be F of X is friendly or something to that effect. And of course, let's go back really quick to the second part, which is if consists of all people, right? And so if it consists of all people, I wish I had more room. To be clear, if it consists of all people, then we do have to specify that someone's in our class. So we'll say C of X, we'll say X is in our class. I know that's impossible to read, but I'm just writing it. And then H of X is the same thing, just the same time. And so I believe that someone in our class. So we're talking about people in our class. We're still talking about someone. And this is all people, right? So this is, there exists someone. And then if they are in your class, there's someone in your class who is in your class and speaks Hindi. I would say that. And that's kind of me improvising, but I believe that would work because someone is in your class and they speak Hindi.
Right.
What do you guys think?
Yeah.
Solid? Cool.
Yeah.
It's been a while, so I don't think I actually covered homework 2, which is funny. Okay, so, and then we'll just do E, which should be our last homework question for number 2, and then we'll move on to homework 3, which is proofs, which is exciting. So no student in your class has taken a course in logic programming. Okay, so I really kind of want to do another exists. I'll tell you what, I'll do this one real quick. There is a person in your class who has not been born in California. So let's say let's see CA, X is not born, or X is born in California. Just put CA. And then obviously there exists a person in your class. If it's the first one, then all we need to do is say, hey, there exists a person in our class who is a Californian. And then that's the first one. And then the second one is going to be all people. So we have to think of everyone.
Not born in California.
Not born in California. Thank you, Adam. I don't know if that not is clear. Not. Yeah, thank you. I was just speed running, so I was not born. And then second thing is there exists a person, and hey, if they have been, so once again, we're just thinking of C and X as someone in our class. There exists a person who is in your class and has not been born in California. That would be the negation right there. Does that sound good to you guys?
Yep.
Yeah.
Cool. All right, last one. No student in your class has taken a course in logic programming, so obviously that would be A. That means everyone. And obviously you're saying no students. So that would be like that. And it would say no student in your class. So L of X taken logic programming. So we would say not L of X for the first one. And for the second one, basically the same thing. We're just saying there is all these people. Well, actually, I think we would still keep the E because we're still talking about some people. No. Let's see. Let me think about that for a second. Definitely this would be C of X and not L of X. Now I know how to do this actually. Let's see. I would say this, and you guys could follow up on me with that. I would say if they're in your class, they have not taken logic programming, and we could just say all people at that rate. So all people, if they're in your class, then they have not taken logic programming, and I would say that is sufficient for that.
Yep.
Cool.
I'd just like to interject. I don't know if this is a hard and fast rule, but something I've noticed with these existential and universal qualifiers is the universal qualifier, the upside down A, almost always is going to use implication
Right.
for its stuff.
I was
And
thinking
the
the same thing.
existential is always going to have an and. You're almost never going to have the and with the universal, because that means everyone does this and that. And that's probably not going to be correct, because there's always going to be some kind of weird exception.
Good call. Absolutely. I will have to remember that one for the exam.
But if you do the implication, it says if they meet this first condition, they probably meet this second condition as well. That's something that applies to, you could probably apply to everyone.
I'm going to write that down. Let's see. So if it's and, then if it's everyone, that's the anarchy symbol, but whatever. That's not my mentor, right? Then conditional. And then exists, most likely you're going to have an and.
Yeah, and I don't want to say every time, because there's probably some weird edge case I'm not thinking of, but at least as far as the homework goes, that's the pattern that I've seen.
Gotcha. Super cool. All right, we'll move on to what everybody's been waiting for. Proofs, which is homework.
Yeah, actually, if you want an exception to that rule, as I just scroll up through the homework, 1.4 number 9 statement C is an example of where you would have a universal qualifier. That is not, it's not an implication. It says everyone does this or that. So then that's just an or statement.
Right. Okay. So that would be
if the domain of X is, it says here X is students in your school. Now if X was everyone on Earth, then you probably can't make that anymore. But because the domain is restricted to your school, you can use this universal qualifier with the or there.
Gotcha.
So that's an example right there of where you don't always just say, oh, universal, let me do the implication. No, it depends on what the statement says. And it also depends on the domain of X. If it's everyone on Earth, or is it a specific group of people, or whatever X represents.
Gotcha. I'm just writing down what you say on the board because I don't know. I thought it was good. Thank you, Adam. Awesome.
Mhm.
Super cool. Okay, let's move on to the next thingy. Unless anybody has anything else they want to add on to, you're always free to. And you could do that while I scroll down to 1.5. Oh wait, this might not be proofs yet. I'm not sure. I started for some reason.
It starts to get into it.
Oh, it starts to get into
It's
it.
not. It's not like the larger ones. It's. I can't remember if it's even called proofs at this point.
What's the issue?
Oh, it's not an issue. I just thought this was proofs, but it's still universal quantifiers, which is still good because I know I still gunk that up sometimes, and I know that hopefully I'm not the only one who gunks that up. But well, hopefully I am because I hope you guys are doing good. But number 7, we'll work on like one of those if that's cool with you guys. Let's do like this one was on the quiz, so this will kind of hammer out 2 birds with 1 stone. And then this, I don't know, just a random one, C, I guess. So TX, student likes cuisine. X, students. Y is cuisine. Express each of the statements. Okay, cool. So obviously, I don't be able to write all that out. But there exists some cuisine. This is how I read that already because Y is cuisine, E, existing qualifier. And then I don't even know how to pronounce that. Mark is his name. Monique. Thank you, Eric. Monique likes cuisine.
Arsene. It's probably French or something where you just kind of leave off the ending letters.
Arsenal.
Arsenal. I prefer Arsenal.
Okay, Arsenal. Arsenal likes some cuisine Y, or J likes some cuisine Y. So I would say there exists some food that I would say either Arsenal likes or J likes, and that's how I'm not going to try to do that with this, but that is what I would say, and that's what we would do. Cool. So then the next one would be every student, or well, I don't even know what this says yet. Every something, and some of something else. So it looks like X is not equal to Z, so there's uniqueness going on here. And then implies, so if something is unique, maybe unique pairs perhaps, implies that, okay, these are people. Gotcha. So for every unique person, every unique pair of students, perhaps we could word it like that. So for every unique pair of students, or if there is a unique pair of students, then, when we have the not here, then we have and we know these both need to be true, and then they'd be false, if that makes sense. So if they both like it, then it's false. So I would say there is a case where if there is a unique pair of students, then they don't like the same food. Is what I'm getting from that? Is that this? Yeah.
What I wrote is for every 2 different students, there's a cuisine that both of them don't like.
Right, because if it was, they would have to both like it to be true.
Yeah.
And it's negated, so it's false.
Yeah, if they're different from each other, then they both like the same thing.
Gotcha.
This one I was a little bit confused on because the back of the book says for every pair of distinct students at your school, there is some cuisine that at least one of them does not like. And I don't know where that at least one is coming from.
Maybe if you distribute in the not, it flips the and to the or.
I guess so. I guess that makes sense.
Yeah, I guess that.
Maybe that's
Because
what it is.
then it would be not T or not T.
Yeah. That's beautiful handwriting. But yes, I agree with you guys. Is that or, and then they're saying you said at least one.
Yeah, at least one does not like.
I'm not gonna write that out. At least one does not like, because they broke that up into there and they converted that to an or, and these are not. So we know that it's at least one does not like. And so I hope that helps people. That's one of the ones I messed up on the quiz, I think, because it said unique pairs and I forgot like this guy. So that's always important. So don't pull a Gabe on that one. Cool with this one? You guys want to move on to the next one? Cool.
Yeah.
23 is my next listed one here. Express each of these mathematical statements, blah, blah, blah. Okay, I'll do 2 of these. So we'll do, what do you guys want to do? I've always been calling them out, but you guys should give your thoughts on this. Which 2?
This is 1.5.
Yeah, 1.5, 23. And then I was going to choose 2 of them. And then I was wondering which 2 you guys
Oh,
would
okay.
do.
Oh, we haven't done these on the homework yet. These are just something new.
Oh, is it?
21 was what we had done on the homework.
Yeah.
Oh, oops. I'm blind sometimes. 21, that's also what I have on my paper. I am just switching
So
up
it
numbers.
looks like 23 is essentially just 21, but with different math things.
Yeah, we could do 21. So 21, use all that good stuff to express the statement that every positive integer is the sum of the square of 4 integers. Okay, I don't know. I'm going to write that here. So we know every, that's a keyword already. Every positive integer, and then is the sum of 4 integers. Okay, we're probably going to want, I would assume, we're going to talk about some integer is the square of some integer, and I assume we're going to want like 4 of those. This might be wrong. I'm not sure. So
No,
far, I think.
you're doing it.
Okay, cool. And then we're going to say, hey, every positive integer is the sum. So every positive integer, so x is greater than 0. So if there's a positive integer, then there is some sum that you could add up. Oh my gosh. Even if I had like a little like one of those ones with the pen, I know it still look the same. So that's fine. Of 4 integers is the sum, which equals x, I believe, right? That every positive integer. Okay, cool. And that's what I would say for that one.
Yeah, I
Cool.
have the same thing.
Yay! All right, perfect. So if anybody has questions on that, let me know. But we'll move on with that one. And 13 is what I have for 1.6. Oh, that's what this stuff.
I think this is where we started getting into proofs, yeah.
Yeah, basically the introduction to proofs. Okay, 13, A and B. Oh yeah. Okay. These are going to be a little longer, and I don't want to keep being super sloppy. So
Do you want to pull up a side-by-side of a Word doc?
I would like to, yeah.
That'd probably work better.
Oh no, Rebecca.
I think you were past
1.8.
it. Oh no, you're on
What?
1.8 now. What?
Yeah, I have no idea.
Man, it jumped.
Sorry about that, guys. 1.6 is this guy, isn't it? No, that's 1.5. Okay, there we go. 1.6, 13. Pull up a Word doc. I wish I could have somebody controlling this. But yeah. So, which one do you guys want to go with out of 13? A, B, C.
Just starting with A is
Starting with
fine
A?
enough.
Sounds good.
Yeah.
Okay. So, I mean, it's right there. So Doug, please let this work. Just let me zoom. There we go. Perfect. Oh, no, stop. One more out, please. There we go. All right, Doug is a student in the class. So we'll just say like SD, or I guess SX, and X is student in class. Easy peasy. Spelled class wrong. That's why I'm a CS major. There we go. And then who knows how to write programs in Java? So we'll do J. So X can write Java programs. And everyone who knows how to write Java programs can get a high-paying job. So H of X, high-paying job, and therefore someone in the class can get a high-paying job. So we have, I have no idea how Adam did that thing before. But I think it's this, and then an arrow. Yeah, to save time, I'm just gonna do this, which I know it's a little long, but yeah. So Doug is a student in the class, so obviously we have SD. And then the next thing we know is that he knows how to write programs, so JD. Then everyone who knows how to write programs, so this is a universal quantifier, which I need to actually find that.
You're trying to look up the code for that. 1 second. If you
Yeah, that would be good. I'll let you do that for a second, and I'll just type the other thing. Thank you, Adam. Everyone who knows how to write.
Oh yeah, if you type 2200,
Yes.
highlight that,
Okay.
like just that number.
Yeah.
Oh no, you can't have any space. It has to be just the number itself, no extra spaces.
Yeah.
And do Alt X
Alt X.
at the same time. There you go.
All right, you're a wizard. I like it. Very cool. That was cool. Man, I'm not gonna get over that. That was pretty neat. Okay, so everyone who knows how to write programs in Java can get a high-paying job. So I'm gonna say
False, but
false.
yeah. That's a joke.
No, that was a good one. I like it. I wish that was true. Therefore, someone in this class can get a high-paying job. Perfect. Okay. So we could say SD and JD. Well, actually, what we could do first, I'm going to break this. This is actually the proving part. So I'm going to break this guy down, and I'm just going to say, hey, we can break that down with universal instantiation, I think it's called. And we could just say this and universal instant. And then
you're replacing the X with
something.
with a specific instance.
Gotcha.
Right.
With some Y. Well, in this case, we probably do want to.
It'd be Doug. Yeah.
Yeah, it would be Doug. Gotcha.
So you're saying if this is true for everyone, it's particularly true for Doug. That's why you're able to do that. If this is true for everyone, then I can just pick someone out of that crowd and put them in its place. And that person in this case is Doug.
And then I'm just going to drag one of our already known stuff down here. And we're going to say, hey, that if they both have the P, then that implies. Can we do that? I have to actually get my paper out for that. Okay. Perfect. I have it right here. No, I don't.
I think you could just immediately apply the modus ponens.
Bonus. Yeah. I just wanted to get the name. Yeah, because I knew we could do H. of D, but I didn't know the name for it. Modus ponens, like that. That's wait, this is
PON.
yeah. Thank you. I was gonna say what that said, but it's kind of sketchy. Okay, and then we could say, hey, Doug is a student, and well, okay. So using that information, we could say, hey, Doug is a student, and they're getting a high-paying job, and then that's what is that one?
That's conjunction.
Conjunction. Yeah.
And then
What was it again?
with that, you can break it up into.
Yeah.
I need an E. And then if you have the actual code for that, that always gives 2. And so that would be like this, I believe. And that,
Oh, the backwards E is 2203. Alt X over the number. Oops.
well, no, that's my bad. There we
Alt
go.
and X. There you go.
Yeah, and Control X. Okay, there we go. And that is.
I'll post this in the resources.
And
here.
it's still h of x.
Oh yes, excuse me. Thank you. Oh yeah, please post that in the resources, Adam. That'd be greatly appreciated. This is existential.
Generalization.
Thank you. Thank you guys. I really appreciate the feedback. I like this back and forth kind of talk. This is cool. All right, perfect. So first one done, and then we'll just do one more because I know you guys. This isn't like proofs, but it's still pretty important.
Yeah, thankfully these ones aren't too bad. It's
yeah,
generally
these-
just remembering what each step actually means.
Yeah, I totally agree with you, which is why it's good to have the resource thingy. So what other
Definitely.
one do you guys want to do out of this one? Like E or C or which one?
Can you explain why it's modus ponens?
Absolutely. So modus ponens, basically it says
I believe it's your given Q for a P implies Q situation.
yes.
Is
So
that
if
what it
it's
was?
like this and this, if you have this and this, then you know basically. Oh my goodness. Sorry. Then you know Q
Yep.
for some X. And so in this case, we can say, hey, J of D, and we already know this one because that was one of the givens.
That was the
and then
premise. Yeah.
This guy we broke up with the universal instantiation. So that's this guy. And we could just think of this basically as a P, and we could think of this as a Q, and we could think of this guy as a P. And we know that this guy implies this guy, and then we get that guy. And so another way of thinking about this is that you could also kind of like say it out, and that usually helps me too. So like if Doug has knows Java, then he will get a high-paying job. Well, we know that Doug does know Java, so hey, that should fill out if the conditional is true, which it should be. Then we know that hey, Doug has a high pay. Oh my goodness, the words. Can you say it, one of you guys?
You can just state the conclusion because you have a conditional statement. If this, then that, and we're told that initial part is true. So you can drop that out and just reference the condition now because it's satisfied.
Oh, okay, thank you.
Okay, if we didn't,
or sorry, not the condition, the conclusion. You can just reference the conclusion of that statement.
Yeah, the conclusion. And if we didn't make that clear, always let us know because we're here to help each other. So if you need like another example or whatever, we got you.
Thank you.
Together. Yeah, no problem. Actually, I was wondering maybe you could choose the next one for 13, since we're kind of up in the air about which one to choose for that.
C.
C? Okay, sounds cool. So I'm just going to get your page, and I'm going to say C. Each of the 93 students in this class owns a personal computer. Okay, so I'm gonna say CX X. Oh, it's computer. Next. I'm gonna say X, just in case, because I see the word student is a student. And 93, I don't think that 93 matters. Everyone who owns a personal computer can use word processing program. So that's the A thing again, and I am not gonna be a wizard. I'm just gonna copy and paste. Everyone, I lost it. Wait, where was it? Everyone, there we go. Everyone who owns a personal computer, X, then, because like Adam was saying, usually when it's everything, it's a conditional. Can use word processing system. So I'll say WX, and that'll be another thing. WX, X can use word processing thingy. Therefore, Zeke, a student in the class, okay, so we know that Zeke, our boy Zeke, the student in the class, can use a word processing. So what we're looking for as our conclusion should be that Zeke can use a word processing thing. So look at this.
That's a good point, actually. Writing out the conclusion you want to reach so that you know it when you see it. I hadn't thought of doing that. I was just working through it from the premises. That's a good strategy.
Thank you. Cool. Glad it works. Okay, so then we'll get to the proving part. And we'll say, hey, I always like to break these up first because they're scary looking. And we'll just say, hey, we know that if it's everyone, then it can be Zeke, because Zeke is a part of the collective that is society. And
Sorry,
so we would say, yeah.
There's an additional premise that I think you're excluding. The second sentence, everyone who owns a computer can use a word processing program.
Yes.
That's another conditional.
Yeah, we have a second one. Everybody who's in the class owns a computer, and then everybody who has a computer can use the word processor. I believe are the two that we are given.
Yeah.
Where do you guys see that? I'm a little blind.
The first sentence is everybody in the class owns a computer,
Yes.
and
The
then
second
everybody who
sentence
has a
is
computer can
Gotcha.
use a word processor.
So everybody in the class owns a computer.
So you need another. Well, no, yeah, you've got it. So then S of X implies C of X.
Gotcha. Sorry about that.
There you go.
That is the blind gate method. So I will break both
Whoa,
of these.
whoa. Sorry, hold on. I'm
Yes.
not trying to be picky, but
No, you're
it
good.
doesn't actually say there's students in the second sentence. It says everyone. Everyone who owns a computer can use a word processor. That's everyone in the world.
Life. Yes.
So it's all computer owners use word processors.
Okay. So would that be just this question? No, that would be.
No,
It's
that one
still
was
a
fine.
conditional. What? Let
It would
me.
be the second. It would be the first one, I think, because the first one still describes each of the students in the class owns a personal computer. So the first one, that one that you're altering right now, is fine.
This.
It's the top one that would have a different. I think.
Yeah, it depends on how you define it. Because I had a P of X, meaning X owns a computer, as one of the functions. So I had a student in class that we have. Oh yeah. So that is you called that C of X. So that's it. And then W of X word processor. Yeah. So you have all the. I'm just trying to translate it from what I have.
No, you're good. Yeah. It's like that.
X owns a computer.
Yay or nay?
No. Well, the first one needs to be students. It needs to be S of X.
First one.
S of X because it specifies students.
Okay, that makes sense to me. Everyone
own a computer, so that implies C of X for the. I do it sentence by sentence.
No,
so the first premise is for the first sentence.
Okay. So each of the 93 students in this class owns a personal computer. So we're solid on that one. And
Well, it's got to. W is word processor.
W is the word, yeah.
So that has to
S
go
of
to
X implies
C of
CX.
X.
S
If
X.
they are students, then they own computers.
Gotcha. Okay, got it. So,
And then the
sorry, guys.
second one,
Everything.
if they own a computer, then they can use word processing.
Okay.
There we go.
Perfect.
Okay, I'm
Thank
happy.
you very much for your help. No, thank you. I'm glad you spoke up. And guys, I'm gonna make a lot of errors here in the future, so don't be afraid to speak up. So thank you guys. Awesome. So does that make sense to everybody now? Sorry, I messed that up. But is everyone getting like how we're getting these guys? If not, let me know and we can clarify that.
You have to be careful. I'm not directing this at anyone in particular, but you know, in English we use a lot of pronouns and implied membership and stuff. So if you talk about a group of people, then you say everyone, it's implied to be talking about the first group. You can't make that connection with these. If a sentence here says everyone, I assume that's referring to everyone globally, unless it says like every student or it's very specific about it.
Absolutely.
You can't assume that they belong to the prior group in the prior sentence unless they're stated as such.
That is fair. That's super fair. So everyone good on that part? Cool. I'll take that as a yes. If not, let me know and we can clarify that further. But then therefore Zeke is a student, so we got that part for sure. Everybody cool on that part? Zeke is a student in the class.
Yep.
Cool. Okay. And then the proving part. So back to this guy. And let me fix that. So we have this guy and we have the other guy. And so then we could say, hey, I'm just going to convert these guys to whatever. We'll say Zeke because Zeke is part of the collective. That is society. And we could say universal. Say the same thing. Except we're going to go with this. Is everyone solid on that part? Does everyone agree with that so far?
You skipped one step, but yes.
One step.
Because you have that. You just skipped the modus ponens that allows you to connect those two implications.
Ooh. What? There's no.
This
This is just universal instantiation. This is working from the premises.
Yeah,
right,
I didn't bring it together.
You aren't able to immediately say that Zeke has a computer up until you do the, because you could say he's a student, so you have the S of Z implies. Wait, let me look at this. Yeah, you have the S of Z implies the C of Z, but then you have to actually take the modus ponens out to be able to say that he does have a computer. To give you the C of Z to input into the next universal initial.
Words are harsh. I get you. I'm with you. So this part, which we know is true.
Well, C of Z for that one, because you know that the S of Z prior to the universal instantiation was true.
Yeah, I'm just putting that there, and then we could say from that C of Z, and that is modus. I'm gonna mess that up every time. Okay, there we go. And that is because we could basically think of this as P, we could think of this as Q, and we could say, hey, this is P. So since Zeke is a student, and if Zeke is a student, then he owns a computer. So Zeke is a student, so that should fill out that condition. So therefore, Zeke has a computer. If anyone's confused on that, let me know, and we will go back to that. And now I'm going to go ahead and go back to this thing. And we could say, hey, out of all the people in the world, if they own a computer, then they know the word thingy. And we know we could break this up now. We can do this, correct?
Right.
And then we could bring down our previous thing, which we got. And basically same thing. So it says if Zeke is a computer owner, then he can use Word. And hey, Zeke is a computer owner, so theoretically this statement is true. So therefore, he should be able to use Word since he has a computer. So we can say, hey, Zeke. We can say the same thing. I'm not going to even attempt that. There we go. And then that is our conclusion. We are happy. I have learned things with you guys, and the world works. I guess
I used a slightly different tact with mine.
Sure.
What I did instead is I had the two premises that you did with the universal one. So the first part is that instead of doing the modest opponents for that, instead I used a hypothetical syllogism to say that if they're a student in the class, then they can use the word processor. So I established C of Z.
Okay, yeah, that works too.
Implies W of, or X, it's X. I didn't even specify Z till at the end. I said it was for a person P, so I just had some hypothetical individual that's part of it. So I said hypothetical syllogism leads to, if they're a student in the class, then they can use the word processor. Then based on the premise that Zeke is a student in the class, that's where I applied the modest ponds at the end. It's the same result. It's just,
Right.
yeah, they
Just
both
writing
work.
it down. That I think I also did that on my first one, on my first run of this, because that's what they had on Slater. And that's what I use to help me understand this better. So you're saying, hey, so this is just basically a copy and paste of our already gotten stuff, and we're saying this goes to here, and then like a Mario
Yeah,
pipe
I
goes to
could.
here.
Well, that's going to be all messy.
And then therefore with the hypothetical syllogism, you're able to just make the jump from S to W.
I could have pasted in the chat, but I also use different letters for my functions and stuff, so it'd be kind of weird to translate it back to this. So, yeah, it's fine.
Gotcha. Does this still look good though?
Yeah, no, that's.
Well, that should be S to W, not S to C.
Oh, yeah, S to W.
Yes.
Yep.
Sorry, because we're taking the middleman out. Yep, absolutely.
And then you're able to put in Zeke, and then just simplify it from there.
WP, and then we could go back to our initial state. So we're just converting basically. Would this be like another thing, or is that fine?
Well, I mean, I stated the premise that Zeke is a student before I did that, but then I didn't actually explicitly state Zeke in that hypothetical syllogism. Instead, I just used modest ponens from those two statements. For me, it was lines 6 and 5. But yeah, more than one we're just in this cat.
Gotcha. Hopefully you guys are not actually skinning cats, but yes, I agree.
That's an ugly idiom, but
No, I'm not. It was just a joke. Yeah, but yeah. So I totally agree with you guys. You could convert this to Zeke because Zeke is a person. I hope, and then Zeke can do that, and then once again, conditional statement. A lot of modus ponens thing going on.
Yeah,
here.
that's
probably one of the most important ones. Just
Yeah.
anytime that you're dealing with implication.
Yeah. So if anybody's still confused on that, let us know, and we will completely try to. I'll try to fumble my way and explain it a little better. But basically, Zeke is a student. Then he uses word. Zeke is a student, so this should be true. So then we just use the final thing. And then if you're a little confused on this, it's just from one of the tables, where basically you could just cut out the middleman and just go from the first to the end. And that's kind of a shortcut. But also, if you're not comfortable with that, there's always this way. Cool.
Page 5 of that study sheet that you put in Discord has the tables there that makes everything way simpler to see.
Okay, cool. Yeah, page 5. I don't want to mess this up because this thing like hops like crazy. But that will be our first thing. And then is this still homework? What is this? 1.6? And 1.6, number 9. That's what I have written down. So we're going to go up there. And of course, we won't do all of these because, yeah, there's a lot. I want to do A, and then I'll let you guys choose one. But A is the most craziest one, the craziest one, not the most craziest. But I'm going to go ahead and do A first, and then go from there. So I'm just going to do like this. Go this time, and I'll say if I take a day off, then it either rains or snows. So we're going to say, hey, dx is X is day off. SX rains or snows. Wait, sorry. Snows. RX. Rain on X day. And what was the other thing that was going on? I think that was the first thing that we have, all that information. Okay. I took Tuesday off or I took Thursday off, so this is now our information. We have, we took Tuesday off or we took Thursday off. So that's one of them. And we have, it was rainy on Tuesday. Oh, sorry, forgot about the first statement. First statement, if I take a day off, then it either rains or snows. So that would be like this. And once again, if you guys have any interjections, just let me know. And then the third thing, I hate that. Okay, third thing, if it was sunny, it was sunny on Tuesday. I'm going to go ahead and just say assume, because this is how I did it on mine. If you guys aren't comfortable with this, then let me know what you guys put. But I'm just going to say that basically it's not, I don't know if that really counts as a not. But anyway, it was not sunny on, or it was sunny on Tuesday. So therefore it could not be snowing, even though it really could, but we just don't know that, on Thursday. Or it was not raining either on Thursday. What do you guys think of that? Yay or nay for that?
Yeah, I mean, I distributed it in, but that works too.
Okay. I'm just going to leave it like that for now because
that's
I think that'll be easier to break it up later. So, oops, that's the wrong thing. I'm going to be consistent. There we go. So, what can we conclude from this? Oh, geez. Let's just bring this up. So
I think there should be one more premise.
Okay, sorry. It did not snow on Thursday. Thank you, Adam.
Yep.
You are absolutely correct. It did not. Oh my gosh, it did not snow. And was this Tuesday? Did I? Yes, this is Tuesday. Sorry, Tuesday, and then Thursday. I don't know why there's a little gap there, but whatever. Okay, so the first thing is that hey, we can start and say we could say all days if you technically want to be. So for any day, if I take a day off, then it either rain or snow. So we can take that first, and I always like to break that down first. And we could just say any day. So let's just say for this case, let's say we just choose Tuesday. It could really be any. It could be Thursday. You could start with Thursday or Tuesday. And I would just say the universal. And then I would carry this guy here because that lets us hammer that out right away. Which this is a little pre-prepared just because I remember this one because it gave me so much trouble. And then from there, you want to use this here. You want to use. That might actually be good. I'm gonna regret that. You want to use modus tollens. Modus tollens. Anybody is confused on that? Is
So that means Q.
When you get not Q and P implies Q,
Yes.
then you're able
Or
to
not P, yeah.
not
That's like
T.
the wrong one.
What is happening? Oh my gosh. What? Bro. What? Okay. Well, anyway, let's just pretend that's in front. And that's crazy. That was weird. Well, that looks clean though. That was nice. then that implies not P. I don't know why it's saying that. Sorry, guys. But anyway, this is modus tollens, if anybody was wondering about that. And basically it's saying, hey, basically a conditional statement you could think of. If this is false, then the whole statement is incorrect, kind of like the truth tables we were doing on homework 1. So if this is false, then no way, Jose, is this going to happen. So we immediately say that's false, which is why this can happen. Because you think of this whole thing as a Q, you think of this whole thing as a Q, and you could think of this guy as a P. So you could say, hey, not P, because this whole conditional statement is false because of this guy. So I'm going to get rid of that. That's all right. And that's also on page 5, like Eric was saying. And so then we're going to go back and we're going to look at what else we got. So just looking here, I'm going to take this, if that's okay with everybody. That's one of the things we could do. And then we could also take this and do Thursday, because that's a day in the week, I believe. And you can do this. Oh, you do this one. Sorry. Let's keep going with what we have already. So we'd say we did not take a day off on Tuesday, and we know that we either took a day off on Tuesday and Thursday. Well, if we didn't take a day off on Tuesday, then we had to take a day off on Thursday. So that means this guy. And that would be, if I'm looking here, it would look like something. Disjunctive. Look like that. That is called the disjunctive thing, where you have basically a not statement and then something with an or, and then you can go ahead and throw that guy in the bottom. And then another thing is that, hey, DTH, we could say, okay, now we're going to go here, and use this that we already got from just this guy, because it's a day in the week. So we're using our knowledge from our answer. Which I'm actually glad we did that, because that flows a lot nicer. And so, hey, this guy and this guy, that's a modus tollens, or however you say that. Modus. So, because once again, has to complete the conditional statement. Sorry, this is going a little slower, but I just want to make sure this is good in detail.
No, it's good.
It's all good? Okay, cool. If not, let me know, because I want to work with what you guys want to work on, because we are a team. And sorry, getting a little distracted now. This guy, and we're going to say, hey, basically same thing but backwards of this thing. And so we're going to use the disjunctive, and we're going to go, hey, it did snow, so it had to rain. And we're going to say, hey, it rained on Thursday. And hooray, we won. And I think that's everything.
Yeah.
Okay, cool. So that one's the worst one.
Yeah.
Worst because it has the most. The rest of these are pretty easy peasy. Some of these were on the quiz. This one, these last two were on the quiz, I'm pretty sure. Or the last one at least.
There is more to the statement, but that's, as soon as you get that, that's everything, because it asks you what conclusions can be drawn from them.
Gotcha.
And so the conclusions are that you took Thursday off, that it rained on Thursday, and that you didn't take Tuesday off.
Gotcha.
But once you get to that point, then you have the day that you took off, you have the weather condition, and therefore you have the other day that you didn't take off. So.
And I'm missing one of them, but yes, I totally.
No, that's it. There's 3 of them.
Okay, cool. Awesome. Do you guys want to do another one of those, or do you want to move on with some other stuff? It's up to you guys, honestly. Because if you think that would be a good thing to work up more.
I'm comfortable moving on.
I'm comfortable too, but it's up to you guys.
What do you guys think?
Anybody have any objections?
And 3, 2, 1. Okay. You can always come back and let us know. Because, once again, we're all here for each other. So, moving on from 1.6, we're going to go to homework 4, which means we only got 3 homeworks left after this, which is super cool. So, homework 4
is the proofs.
Homework 4 is the proofs, which is what everybody was scared on, including myself, which is fun. I'm also kind of scared of those things that we just did because I don't know. I don't know if he's gonna like throw a big hard one like this. I mean, this wasn't hard because we were all working on it as a team, but sometimes
I feel like he's not going to throw anything
like
too
that.
in depth with those ones.
Yeah, I hope not.
I think it'll be more like the one that we had done like right before it.
Gotcha. Okay, 1.715. So let me scroll down. Now I'm gonna leave this Word document up in case we need it. Hold on, I'm gonna go through the page. That's not good. Oh. That guy looks cool. It looks like he could be in a movie. Kinda. He looks like he could be like Han Solo. Like he's got like the.
Yeah, you're
he
not
doesn't look
wrong.
Like a math guy. Yeah. It's cool.
That looks like a headshot from a celebrity.
Yeah, it really does. It's crazy. All right, 1 point. I'm on 1.8, so I scrolled too far. There it is. Okay. So yes, proofs. Hooray. Number. What do I have? Number. We could do this whole thing honestly if you guys wanted to, but I'm going to start with number 15, which I think is a conditional or a contradiction. Proof that x is this the right one? Yeah, this is the right one. Okay, so 15, it says prove that if x is an irrational number, then x is greater than 0. And x is greater than 0. Then root x is also irrational. So we have, we could say our p is x is an irrational number, and we have q, which is square root x. Sorry for the weird way I wrote that. Is irrational. And you could also say like positive or something because I think it says x is positive.
This is 15, right?
Yeah.
So I don't know how in detail he's looking for here, but normally we could do this. This is called a direct, which is where we just have our thing. It's called direct. We have our thing, and we just try to solve it. But obviously, irrational numbers, they're kind of wonky, and I don't really, to be honest with you, I don't even really, I have no idea what the.
I think direct proofs are going to be difficult with irrational numbers.
Yeah, I
think
agree.
it's easier to do something involving rational numbers. So contradiction or contraposition or something like that.
I agree. Want rational.
Yeah, was it like proving the contrapositive or something like that?
Yes,
Yeah.
I agree. That sounds solid. And I hope that this works this time, please. Question mark. Yay. Okay. So we're going to do the contrapositive, like I believe Nathan said. Sorry if I got your name wrong.
Yep, that's correct.
Nathan? Okay, cool. So like Nathan said, we're going to do that because I agree with him 100%. And that would be obviously the inverse, which would be is rational. And if we can prove that, then we are cool beans. So, how would I do that? I kind of want to draw for this one, if that's all right.
So then that says if the square root of x is rational, then
Yes.
x is positive and also rational.
Yes, that's exactly what I'm going for. Yep. Okay. So I don't know if I should write. I'll just write that. All right. So square root x is rational, which means that square root x equals p over q, and p over q. Q cannot equal 0. I'm just going to write it and see if that's okay with everybody. So q cannot equal 0, and yeah.
Q has to be. Oh yeah, you're right. You're right for the rational numbers. Yep.
Yeah. So q cannot equal 0, and then p and q, I believe, are integers. I may be wrong on that, but for rational numbers, let me know if that's not the case.
Integers with no common divisor.
With no common divisor, and I believe that was Aiden, I think. So thank you. And then we are going to do, so we just, obviously we're assuming not q. And then we're going to go ahead and square both sides and say, hey, squared, that's going to be x. Okay. And then we know that obviously if q cannot be 0, I mean, it's still the same thing, because if you kind of look at that, there's no way that q could magically become 0 in this case. So really that's almost like a new constant, like s over t or something, which is still a rational definition, because t is still not equal to 0, and s and this, but with s and t. And then I would say positive, and then yay. So that's what I would say. And I know I can't do the tombstone thingy, but you guys could feel free to do the tombstone thingy. But I think that would be fine for the test, because we're just
Posted the if you wanted to do the tombstone, I posted it in the chart. It's 220E, capital E.
Oh my
in
gosh.
in resources.
Yeah, 2202 capital.
No, just 220E. There's not a third two. There you go.
Gotcha. And Alt X. Hooray.
Yeah.
And yes, you are allowed to use emojis. No, not really. Okay. So next one.
So for contrapositive, we're trying to prove negative q implies negative p.
Yes, absolutely. So that's contrapositive.
And so if we're able to prove negative q implies negative p, then we're saying our original statement was false or true.
So we're
Not
saying
Q implies not P is logically equivalent to P and implies Q.
Okay.
If you look at the logical equivalences chart in the Discord on the resources page, you'll find that there.
Okay. Thanks.
okay. Next. We are talking about number. What about 1.7? 25. 25 is the next one I have. Yes, this one is not fun. So show that at least 10 days. So I'm going to just get our mind fresh and we're not thinking about that anymore. And so show that at least 10 of 64 days chosen must fall on the same day of the week. So I just know that it's contradiction, and I know that like I should have like a reason on why that is. But in my mind, it's kind of like you can't break it up to be P and Q, because it just kind of like looks like one statement. Like show that at least 10 days. It just seems like it's one big P. You kind of think of it. And so to prove for contradiction, I believe, let me know if this is wrong, but oh my gosh, spell it correctly first. Okay, there we go, contradiction. So you have to assume the statement is false. And then if the requirements don't match, there's a fancier way of saying this, of course, but basically, if you're gonna like break it down to the very beginning, if the requirements don't match the given, then it is proven. Then there's a contradiction, which is why it's called that contradiction. And so the statement must be true because then it can't happen if that's not the case. So for example, I'll try to make this super clear. So show that at least 10. So x is at least 10, and we'll say days. Any 64 chosen must fall on the same day of the week. Oh my gosh, super steep here. There we go. Okay, so if we're assuming the statement is false, then we're going to say, hey, this guy is less than 10 days, because the opposite of that would be less than 10 days of any 64 days. So that would be the negation of that. And so I would say, hey, this is the opposite. And so we're assuming that the statement is false, which is here. So statement is false. And then we're going to say, okay, well, that means the max number of days we could have. And once again, I memorized this one because it gave me so much brief.
You have the same statement twice.
And which one?
You have days less than 10 and days less than 10.
Oh, you're right. Thank you. Thank you. Awesome. Thank you, Aiden. Days greater than or equal to, I believe.
Yeah, at least.
Yes. And so we could say, hey, 9 times any given day of the week. I think there are 7 days in the week. So that would be 63. And 63 is a little too small. 63 is less than 64. And so we have a contradiction because we have to have at least 10 days or greater to be true. So we could say, because there is a contradiction, being 64 days are chosen, which is our given, then original statement is true, smiley face. With that's just easier than the tombstone, but I'll throw it there. Okay, so that's, if anyone has any questions on that one, hook me up, or if anyone wants to add on to that, feel free, because we're all in this together. So just let me know, or let everybody know, I guess. And if not, I'll move on to the next one, and I'll look at which one I have labeled next, which is 29. That's this guy. I wonder if copy and paste works. I feel like that doesn't feel my brain is engaged, though. Let me scroll down. Do that. Okay. Prove that
It should
input.
work as long as there are exponents. It doesn't transfer the exponents.
Gotcha. Looks like it works.
It'll collapse them down into
Just a
coefficients.
number. Like this. Oops. We'll just do that. That happens a lot on Discord, but luckily we don't have an exponent in this one. So prove that if blah blah blah, then blah blah blah. So obviously we have P and we have Q. Doing like that, but okay. So okay, this one, a little bit of hoop jumping, because I think I made this a little too complicated just now. Basically, I was in the professor's office hours for this one a while back, but if you have, I believe, we're gonna get a little nitpicky here, but this is called a trivial proof. If Q is true, that is not a Q. If Q is true, then the statement is true, which is what we know just from the truth table of conditional. And so really, if we're thinking about that, we could just care about this Q statement. Because if we prove that this is true, then we can just say, hey, trivial proof, and knock that guy out. But I don't know how detailed, because when I asked him, he said, no, all you have to do is prove this, and then you could just say proven by biconditional, because you prove one and then the other. But if it's like a question in there, you could always prove it that way too. But basically, that's why I'm going to ignore this P just for reference. And I think that was a lot of the homework, because that's what I ended up doing after I asked him about that. And so we just care about this. So n is odd if and only if by then. So if and only if, that's a biconditional. I have no idea how to do that. I'm sure the wizard will tell me in a little bit here. But I'm going to leave it like that. And so that means we have to say, when it's biconditional, you have to prove that. And you also have to prove the other way. So this guy. So n, we're assuming. Did I skip something? N is odd. Excuse me. I was like, n? N is odd. There we go. It's like, how do I prove n? N is just n. There we go. Okay, that makes me feel a lot better. So we're assuming that n is odd. So n equals 2k plus 1, which is just odd. That's just a definition. That's also on the resources page if you want to check that out. And then we could just do a good old plug and chug. And we could say, hey, this guy is doing that guy. And so then, oh, I'm just going to put equals. And I'm basically just going to say that this becomes 10, this becomes 5. I'll just put 11 because that just adds up like that. And then this guy, actually, sorry, I shouldn't do that because there's an important thing that happens here. And then you could break this up into this, I believe, which is 5k. Oh man, what was the thing with this? This combined to 10. So this is 11, right? But you could technically say that's 11, which is 10 plus 1.
Yep.
And then plus 5 plus 1. Oh my goodness. Sorry. Plus 5 plus 1. And then that equals 2 to the n, or you could say k, or you could say even g, plus 1, which is the definition of odd. So that one is
I was
proven.
gonna say 2G is pretty outdated by this point.
That
Joke.
was a good one. Okay, I like that one. Okay, so then we're going to do the same thing here. And we're going to say this equals, well, I mean, I think we could just actually break this down, can't we? This one, what are we going to do for this one? Are we going to reduce it, I think?
Use
I don't
proof
see
by
that one.
contraposition.
Use proof by contraposition. Thank you very much, Aiden. I completely forgot. So use exactly what Aiden was saying. Use proof by contraposition. And so that means the opposite.
So wouldn't this whole thing just be a proof by cases wherein you're checking if you give n as an odd number and then n as an even number?
I would say so, yes. I would absolutely say that's fair.
Because
But
that's
then,
the way that I had done it instead of trying to prove the biconditional, because we're just testing odd or even. So I was just proving that if it's odd, then if n is odd, then 5n plus 6 will be odd.
That's what
And
it
then-
ends up being. Yeah.
Yeah.
that's cool. Yeah, I was just going with the back of the book, but yeah, that's definitely a more efficient way of breaking that down. So you can do that too. And then obviously I'll just do this really fast since it seems like everyone has a solid grasp on this guy. 2k and the 6. And then we go, hey, that is the 10. And the 6 And we could say, hey, take out a 2 and yes, 5 plus, I zoned out for a second, sorry. That's 2k, which is our 2 b or whatever, because you can just break this whole thing into a variable, and that is also equal. So we're happy. Good job. Okay, next thingy. Anybody have questions on that guy? Okie dokes. So, let's do 5 for 1.8. And if anybody has questions on 1.7, like another one that they want to do at 1.7, let me know. And we can absolutely hammer that out. Let's see, 5 and 7. Man, it's already 12:30. Goodness gracious. Time flies when you're having fun. Okay, so we will do this dude. Prove that if x and y are real numbers, then max thingy. Use proof by cases. So it tells us what to do, which I really, really hope that is the case on the exam. And we could just say, hey, case 1 is exactly what they told us to do, which is good. No, that's not what they told us to do. This is what they told us to do. Okay, so let's just do that, and we could just say, hey, this guy. Max of this, if x is greater than, is going to be x, and then min of y is going to be y if y is less than. And so that actually just gives us exactly what we're looking for. But I guess technically, if you really wanted to say, get nitty picky again, or nitpicky, I'm gonna have a difficult time with that. You could say x equals y in that one case, because it says equals. Then technically you could say like xx, I guess. And then technically they're both equal. So since x equals y, you could just say x plus y again. Which equals y plus x, and yada, yada, yada. So you can do that too. But anyway, we're happy. That one was, that was the easy part.
And yeah, if x is greater than y. Yeah,
Yes.
exactly.
Yeah. Okay, cool. Cool. And then if x is less than y, we have basically this guy, which if it's min, if it's max, we'll start with max. Y is greater than, so y. And then x, well, x is less than, so x. And that's also equal to x plus y because of just kind of mathematical moving around of some stuff. And so that one is solved, and we are, again, very excited. Okay, cool. So that one was good. Any questions on that one, let me know. Always just feel free to stop me. And then 7 for 1.8, 17 or 7, and 7. I have 7 written down. So let's
I think it was 7, yeah.
Okay, 7. And once again, if you want to do the other two in here, these two guys, we always can. But I just chose these because they look a little more gnarly than the other ones. Gnarly being not fun. Okay. So this one, proves using the notion of without loss of generality that thingy and that other thingy is what that is. So we're proving this, and we're proving this without loss of generality. So once again, kind of memorize this, but without loss of generality basically means you're gonna ignore the case where the same result would happen. So in this case, you want to say, hey, this guy, since this is the case, you can basically say, hey, it doesn't matter if y is smaller than x or if x is smaller than y, because it's ABS, and absolute value is just going to make it positive anyway. So through that, you could say you use without loss of generality on x is less than y, and so we'll just use that, and we don't have to consider the case where x is or where y is less than x. And so I'll make that a new thing. And once again, this also gave you some grief, so that's why I'm kind of speed running up a little bit. But if you guys need to slow down the video. Also on Discord, Aiden is a math major, so he's very good with proof. So if you have any questions on proof, I would highly recommend you DM him for stuff, because I think he's a pretty cool dude with proofs.
Took a class like this before, so
Yeah, and you post a lot of pretty good stuff about the resources and stuff like that. So yeah.
So with your statement really quickly about without loss of generality, should that be reversed? I'm too tired to think right now. Should that be saying we don't have? Shouldn't we say we don't have to think about x is less than y? Because if we're getting rid of the absolute values, we want x is greater than y, right?
Yes.
That's the one we want to be working with?
Yes, that sounds good.
Okay.
So we're considering the case where y is greater than x in that case. Does that go with everyone?
Wait.
I always use x greater than y just for this case.
X
Yeah,
greater than
no,
sorry.
I was,
Sorry.
yeah.
Yes. Okay. I'm
Wait,
getting a little
that's the same
tired.
Wait, you wrote
We
Oh
wrote the
my
same
goodness.
thing.
Okay. X is greater than y.
There you go.
Yes. Okay.
And we are happy. Okay. Alrighty. Cool. That sounds good. Okay, so in that case, because we're only considering that one case now, we can also say equals to, I guess, technically, if you really want to. I don't think it matters. But I'm just going to use greater than. Because
So your statement of without loss generality, where you're saying like ignore the case where the same result would happen, you're speaking about how a negative and a positive would end up being the same in an absolute value, correct?
absolutely, yes.
Okay.
And so even if we went with the other way around, we would still get the same result here. And I'm going to show you how that's going to happen. So x plus y minus. So if x is greater than y, then we can just say we're just going to leave it like this. X is y. We're going to break it out of the absolute value. And then this negative is going to FOIL into everything. So this is actually going to be plus. And then divided by 2. And that is going to equal. So logically, we know that the min is going to be y, because y is a tiny lad in this thing. And so breaking this down, if you just kind of look at it, the x's cancel out, the y's add up just to save time into 2y, and then we divide by 2, and we are going to get 1. So hooray. And then we're going to just bring this down here. And we know that max y, or max of that thing is x, because we're considering this case. And so if you think of that, and we have, I'm not going to do that. We have this guy. Boom. Then we have plus. So once again, we can just eliminate the absolute value. And the y's cancel out, as you see here. And the x's add up, and divide by 2. And we get x. Now, just a really quick thing, if x was, I'll just do it on 1. If x is less than, just to prove that this is kind of the same thing, min of y would obviously be x. And so then we have this guy. And if x was less than, this is going to be x somehow. If x was less than, what is, how is that at a different angle? That's weird. Okay. If x is less than y, then it's obviously going to be negative minus y. So you can flip these around. And basically, you have y minus y and x plus x, and then kaboom. And if anybody has questions on that, then
So is this essentially what we would be doing if we weren't using without laws of generality? If we wanted
Yes.
to test it just off of cases, we would do it where x is greater than y and then if x is less than y?
yes, this would be your case 2. This would be your case 4. But we can ignore this case because of
Right.
W, yeah. And so in my mind, I could see how people could get kind of confused of how this switches when x is less than. But I hope it makes sense that since this is a negative number, wait, it's not a negative number. How would I explain this? Anybody have a better idea of how to explain like why it's negative?
The inside of the absolute value is negative, so the negative makes it negative. So if you just say, hey, the negative of the inside, then you're good.
You're good.
Because that
Yes.
just gets you a positive. Because that's what you're doing there. You're just evaluating the absolute value.
All right. Sounds good to me. If anybody has questions on that, just let us know and we can do that. But does anybody want to do any more proof stuff? Because we finished homework 4 and we can move on to homework 5, but I want to make sure everybody is happy with that. And of course, we'll also be going over a, where is it? It's in the resources one. But there was one where Aiden was talking about last session review where we were proving something about the square root of 2. It's once again, it's in the
Right.
resources document, but it's we were going to go over that later. But if you want to cover it now, what do you guys recommend? Do you want to cover it now, or do you want to cover it after?
I mean, since we're on proofs, we can cover it now.
Sounds good to me. Okay, so we're opening up this guy,
I think you have it on the contradiction.
the contradiction. Okey dokes. Scrolling. And sorry for this gives you a headache. This one. Okay, so obviously we want to like cover it up somehow, but let's just not cover it because that'd be a hassle. So we want to prove that square root of 2 is irrational, and this will also help because it's in good handwriting. So suppose square root of 2 is rational. So contradiction, right? So we're assuming the statement is false, and then if the given of what we have is not the case, then there's a contradiction because we need to have the given. So we're assuming it's false, which means it's rational, and it's a over b, and a over b, like I even was saying, have no common factors. And so if we do that, we can square both sides, and that's why they have 2 equals a squared over b squared, and then they have that thing, and obviously a is then even, and b is also even, and hey, if 2 things are even, then they have common factors, and that contradicts the statement of rational. And so that is a contradiction. And we have proved that by contradiction. That was a little bit of a speed run, so I was going to leave that so people could kind of look at it. It's always in the resources as well. And I'm going to drink this water because my throat is dying.
So because we have a squared being equal to 2b squared, we are showing that a is therefore even, which can then be replaced by a different showing to make it more obvious that b is also even.
Yes.
In this case.
That's
and then because they're both even, they're both divisible by at least 2. So therefore, they have a common factor.
I would say so. I would
That makes
say
sense.
absolutely. The only tricky part, I think, in my opinion, the only tricky part for me was understanding, just like the absolute value. The tricky thing is this part, where you have to say that, hey, this is also equal to 4c squared. But basically, you could just kind of throw this in there if you really wanted to, because you could say, hey, a, and basically what they're doing is just putting another value. I believe
Right.
this a equals 2c, and then there you go. Because it's just some constant, an a squared 2c, and you're saying 4c squared. And then there you go. An even divided by an even is a common factor. And there we go. Okay.
That makes total sense.
Coolio. So I'm gonna close out of that one. We're gonna move on, unless anybody wants to go over one more proof thing. Or of course we can always do whatever. But just let me know, and I will scroll down while people are thinking of what they want to do. I will scroll down to homework 5, which is 2.1, which I believe is sets. I don't know where I am though in this book. Super. Okay. Cool. Hooray. Okay. So 2.1, here we are, sets, easy peasy. Well, not easy peasy. I don't want to say easy peasy.
They at least make more sense than the proofs.
They make it that, yes, compared to proofs, a little easier peasier. But of course, everybody has their own different struggles and stuff. So I don't want to be rude.
That's true.
But yeah, so sets are super important, super cool. I have specific problems that I think are pretty good to go over them. But the reason I feel confident on proofs is because I'm actually taking or on sets is because I'm taking a sets class actually for my math minor. So that's always fun. And I know some people aren't, obviously. So we want to go over them. Because, yeah. Okay, so this one, I was thinking we'll the first couple of questions kind of go like repetition. Like, if there's a 1 in there, and I would just say for these ones, I was going to kind of skip these ones, but feel free if you do want to go over these ones, let me know. We could always go over them. That repeats are always allowed, and that you could basically just reduce anything in a set down to its just repeated values. And also be aware of the curly guys, because they are not nice. So if you have curly guys, that is not 1. It is the set of 1 that's included in a set. I don't know how to explain that. But if somebody has a better idea of how to word that. And like same with this one, like this is not 1. This is the set within a set of 1 and
Right.
1. It's not just the element 1. So 1 is not in there. 1 is not in this whole thing, unless it was just specifically 1. And this guy, same thing. Like even though this looks the same, you gotta look out for the curly guys. That kind of goes with this whole question. Just be aware of that. Be aware that this set can also this null set I think is normally 0, but it could also cardinality. It could count as 1 if it's in a set. So like in a power set, for example, you could say like power set of 2, and I promise I'll get back to typing because I know that typing is probably better for this kind of stuff. But you could say power set of 2 is the null space along with, and we'll get the power sets in this as well, of I believe the set of 2. I think. Let me know if that's wrong, but I believe it's like that. And so this would actually be 1, 2, because even though that's like that, this is 2 elements. And so I would say the cardinality of 2.
Well, that would be the power set of the set containing 2, but you just said power set of 2, which has no meaning.
Gotcha. The cardinality.
So inside the parentheses of the power set thing, on the left, you would want to put that it's actually a set. So the set containing 2. Did he mention
Yes.
anything about the cardinality of power sets?
I don't think so.
Like the general rule for it? Okay, well, so the general rule for it is the power set is going to have a cardinality equal to 2 to the n, where
Okay.
n is the cardinality of the set you're taking the power set of.
Okay, so for example, I'm just kind of following what you're saying here. So if you had, and I see what you're saying.
We didn't really go over power sets like at all.
We
I don't
did.
think
It was
we
on one of the
did that
homeworks.
Was it?
Yeah, it was homework number. That was one of the ones I was going to get to. Homework number. We don't need to spend too much time on it.
You very briefly touched on them.
This one. 43 question mark? I'm not sure. 43 or 41? Maybe. 43. No. 41. No. Oh, maybe you didn't. Anyway, A and Q type, what you were saying, and you were just saying it's n and then n cubed, and then we'll move on with the stuff.
Yeah, so whatever the cardinality of the set you're taking the power set of, so that's 2.
And yeah,
The power set is going to have 2 to the n cardinality, so that'll be 4. So,
cool.
and so obviously that will be the empty set, the set containing 1, the set containing 0, I think that's a 0, and the set containing both 1 and 0. So
Perfect.
4.
Thank you. Okay.
Mhm.
And then we will get on to the other stuff. So watch out for curly guys. If they ask a power set, which is very unlikely, like Eric mentioned, which I agree with Eric too, but it's always just in case. Good to be cautious. But I completely agree with Eric that they're probably not going to ask that. But if they do, just keep that to the end thing in mind. Going to actual one of the problems, we'll say 19. So 19, this guy, suppose that A, B, C are sets, and A is a subset of B, and B is a subset of C. So that basically means that if X, how do I say exists? I would say if X inside A, then X inside B. Because basically how I always think of it is like we got a donut. So we got a B. This is the one time I'll use with drawings. And we have an A. So A is in here, B is out there, and that is the subset. You could always think of it like that if you wanted to.
The element of symbol is 220A, it looks like.
Boy. Yay. Thank you. Okay, cool. We could just say that. And then, okay, so then same thing with B and C, right? And so technically, if you want to break this up, going back to our previous thing, we could say what Adam was saying with the whatever this is.
Hypothetical syllogism. Yeah.
Yeah, that thing. And so you can say this is this. And you could do it that way if you want. And also, what I actually did, I did a doodle. And I don't know why that was allowed, but I did a doodle and I said, hey, this. So that's how I did it. And I got full points for that. But I don't recommend that on the midterm. I recommend actually like proving it. That's what I did on the homework. Because I just said like, hey, if that's in there and that's in there, then this is in C. So then we're good. And so that's what I would say. And yeah. And moving on to the next question. Sorry, one sec. Okay. Sorry about that. Next question I had listed was 41. So 41, explain why this and this. Okay, yes, I like this one. Mostly I'm just going with the proofs of the sets because I think that combines a lot of people want to go over proofs and kind of two birds with one stone kind of idea. So AXB is basically where you're doing a FOIL, where you have like, I don't know, you have like 1, 2. Sorry, it's kind of gross, but if you have 1, 2 for A, and if you have, I don't want to do anything crazy, I'll just say 3, just to save time. Then you have basically 1, 3, and you have 2, 3. So you're basically just foiling out, and the larger it gets, the larger your cardinality is going to get. So that's why I didn't really go too big with that. And so explain why ABC is not the same as this. Well, if you broke this up first, and actually perfect, I'm glad I did that because now this is going to be easier. So let's say C is 4, just for ease of living. If we did that, and then we did XC, so obviously we did this first, and then we did XC, then that would actually look like this, where we're foiling again. So we foil this value with this, and we foil this value with this. So that would actually look like this. That's not a curly brace. That's just that was a pinky slip there. There we go. And just let me know what you guys think of this. So this is that. And then if it was actually this guy, we would say, yeah, we would say we would go into a lot of stuff.
It's an ordered triple, right?
Yeah, it would be, so these are, so in this case, this is
As opposed to a pair that has like a, not really a subset, but like one of the coordinates is.
yeah. So in the book they call them duplets. So this guy is a duplet because there's 2 of them, and then this, because there's technically, this is just 1. This is just 1, and then 2. So this is a duplet, and this is a duplet. Well, this is a triplet. And right away, I guess right away we could just say, we don't have to really do the rest of that. Right away we could just say, hey, this is a triplet. Well, that's not in there, so we're done. And
Yeah.
so yeah, and so those are not equal, and the world is at peace, and we're happy. So I just really wanted to use that emoji again. Okay, so then that's what I have for that one. And 43 is this guy. Oh, this was the power set. This one, which it wasn't really like doing a power set, but it was. Oh, jeez. Let's just say P. Let's say P. That's it. There we go. Okay, so once again, oh my goodness. Power set, like Aiden was saying, power set of A. Let's just
You
say
wouldn't just
is-
copy over the same sets that you used.
Yeah, it's good. Thank you very much. That's a smart idea on saving time. And I want to be a time saver. I was way too high. Oh my goodness gracious. Where was it?
No,
That
you were
did-
there. You just highlighted it.
Did I?
Yeah.
Oh, yeah. Oh my goodness. Thank you very much. Thank you. Sorry about that. I'm just gonna use 1 just to save time. I'm just gonna use simple 1. Because that will do the same thing. And so the power set of A, as we described earlier, is just going to be the null, which I don't know what that is, sorry. And that is going to be like that. And of course, that's going to be there we go. It's going to be like that. And then same thing for B. So just save time. We'll do that. And then we're going to say, hey, cross those guys. So we're going to do this. And doing that will result in some really gnarly stuff. We'll just do 1 just to prove what's going on here. So that'll look like that for one of them. Oh, we'll do 2 actually. Sorry, that was a bit of a lie. There we go. And then another one. It's the same time. And then we'll do this guy. So this guy, obviously, they're crossed first. And so if they're crossed first, then we're going to do just 3. Easy. And then if we're going to do that, then that would be obviously null, comma, of that set, which is not equal. So it's not equal. Okay, that's good on that one. So I'm going to move on to 2.2, unless anybody wants to bring up anything that they're confused on.
I think we have to hop off and get some lunch. But
Yeah.
I'll catch you guys later.
Okay, no problem. Have a good one, Adam. Yeah, I was gonna end this review session at 1:30 because I know someone has a lab that's actually in here right now, and someone else had to do something at like 2. So I'm just gonna try to speed run these next few homeworks. Well, not speed. I still want to. If you guys have any, I don't want to leave you behind. You know, or if you have a question, I don't want to ignore you either. So always feel free. This is still 2.1, isn't it?
Really quickly, there's a rule which I think he never mentioned, but might actually use.
Yes.
Any set crossed with the null set. So like if you do A cross null or you do null cross A, either way, no matter what's in A, that will always give you the null set.
That was actually that's
I think
perfect.
that was a rule that he
Yeah.
put on one of his slides.
Oh, he did say that? Okay.
It was
think
one of the
so.
homeworks actually. It was I think it was 19.
Okay, perfect.
Might as well hammer that one out. No, it's not 19. It was 31.
Just because that just came to mind and it's like, oh no, what if he puts that on the test?
It was one of the homeworks in 2.1. It was one of the homeworks in homework 5. But yeah, I
Alright, cool.
totally think that is important. So I'll just write that there.
All right, great.
So show that if A and B are sets
I think
in
it's
the universe, 33 and 2.1
Yeah, in 2.1, I'm pretty sure.
and 2.1. All right, it's 33 and 2.1. So that is where am I reading? 17. Sorry, guys. 17. Okay. So this is a proof thing. This is another kind of.
I have a kind of like a dumb question. What does the
Oh, yeah,
sideways U equal mean again?
That is
Subset.
so that's subset, and
Oh,
that
okay.
basically, yeah. So that's just we can scroll up and I can. Where is it? Oh my gosh.
I think
Yeah,
that's
here
where
it
you
is.
had started it.
Yeah, right here. So subset, and you could basically think of it as a doodle, and you could go, hey. So here, A is a subset of B, so you could think of this as A, and this is inside B, and so therefore any element in A, if this
It's
is
also
there's
in
an
B?
X is also B.
Right.
Okay, perfect. Thank you.
Yeah, no problem, man. No problem. Feel free to ask questions, guys, because we're all here for each other. And so let's
That's
do this.
supposed to be a complement union B equals universal.
This guy.
Yeah.
Yeah, it's a complement.
I will do this.
No idea how you're supposed to. Yeah,
Yeah,
Yeah, I'll
that
do
works.
that works.
Yay. Okay. Okay. So we'll do show that if and only if. So if and only if we know that in proofs, this is actually a proof that we have to prove P implies Q, and we also have to prove the opposite. So that implies that. And so, that's the key word. If you're thinking about show, and it says if and only if, you're like, dude, I have to do this and this. So to do this one, we're just kind of looking at it and saying, okay, this is a subset, and this is going to be not a UB thingy. Okay, so this one, we know that if there's an element, if X in A, then X in B, right? So we could say in the universe, we could say X is either A or not A. And then going with our what our assumption is, if we choose to say X is in A, because we kind of know what's going on there, then it's in B, because that's just what we're given, the subset. Think of like the donut. And so we could say, is in A. And we can say X is in B. All right, cool. So then that basically means we got B, which really means in the whole universe, we can have B, or we can have not A. So if X is not A, then X is I don't know, not in A. So you need those two. You need both of those statements to have the universe, right? So that means that we have to have the union of B or A, or not A, excuse me. Because if it's in A, we know it's in B. Then that's the universe. And basically, I believe that proves that. Because we could say, basically, you could think of it like this. So A or not A, if those are unioned, then we have that, which is actually a definition of one of the laws. And then we know that if it's an A, it's in B. So we basically just did substitution. And that's how we proved that that was going on. If you have any questions, let me know. But substitution, because we used our assumption that when it's in A, then it's in B. And this is just a law that we know from the table, which is in the resources page, which covers the whole universe. Cool. So we also have to prove this. So first part done, and we're happy. So next part. So not A, not B. Okay, so this part, again, just for simplicity and for speed, we're going to say that if X is an A, because we can choose one of them, if X is an A, then X must be in B. So how did I come up with that? So right, so if it's not an A, but X is in the universe, so then if it's not an A, but we're saying unioned together is U, then there has to be some, it has to be in B, because otherwise, I wish I could like draw this better. But let's say you have an A in here, and you have a B. And basically what we're saying is, hey, we're choosing not A. So we're choosing everything outside of A. But we're covering the whole universe. And so we have to be in B. I feel like I'm not making sense, so I'm going to ignore that drawing. And I'm just going to say, hey, X is an A. That has to be the case because we're still talking about X existing in the universe, and we actually need this to be in the universe. So this has to be in. I hope that makes sense. I know I repeated that a bajillion times, but basically,
No,
this
yeah, this is
means,
making sense.
Oh, Aiden's also drawing something. Go ahead, Aiden. This means that yes, exactly. Aiden's doing that stuff on the side.
Oh, I was
100%.
muted. So here's A, and then if it lets me draw again, we see that, and this is just a thing that always holds. Not A is union, or not union, universal. So everything minus A, so it's everything out here. So if we're already considering all of this, and then we consider some, I don't know how I can pick a different color, but I'll just undo that now that I have it there.
A different color. I think you
And
should
then
be able
if
to
we
pick a
consider,
Or you just stuck
maybe.
around.
But so not A is everything. I'll try to do cross hatchings, I guess, like that. And then B includes everything like this, which includes A. So hopefully that makes a little sense. So it's actually everything, and then everything in B that's not in A is actually counted twice. But yeah.
That sounds good to me.
Yep.
Would be a little better if you had different colors, but I get what you're saying for sure.
Yeah, I don't see how to pick different colors, but
No, you're good.
oh, now I see it. Okay, I'm done.
You're good. It's the thought that counts.
Yeah.
The thought that counts. Thank you, Aiden. Okay, so I'm going to assume that everybody's good on that one. So then we're going to move on to 19, which is kind of the same thing, except we're doing some Boolean stuff. And of course, I'm going to move down because it kind kind of stresses me out when there's more than one problem on the page. And so, once again, this whole thing is knotted. Excuse me for that. We're just going to put not. And then we're going to, oh my gosh, we're going to say not A, not B, and not C. So, show that blah, 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 blah. All right, so to prove that things are equal, you must prove that they are subsets of each other. Because if you think about it, if you are a donut and you are equal to a B, then technically, let's say this is B, and it's the exact same thing, and this is A, just pretend it's like on top. Then A and B are the same, they're occupying the same space, and so therefore they are subsets of one another because they are inside of each other. Donuts inception. And so that's exactly what we're going to do here, and we're going to prove it by using the laws, the equivalence laws. So we're going to break this guy up, and we're going to just go ahead and use the Morgans. And we are going to, well, okay, technically you can't do that. Technically, you have to say the law of, what is that, intersection? Intersection definition. And basically you just turn these guys pointy, which is the or. It's a can't remember the name of that, but it's the
You mean conjunction?
conjunction. Thank you very much, Ian.
Yeah, that's an and.
Sorry, an and. Goodness gracious. Thank you very much. Yeah, exactly what Ian is saying. An and, you turn a pointy. Law of intersection is and, which is conjunction. Because I messed that up. I don't want to confuse people. Because I am being silly. And now you could say De Morgans. And in De Morgans, you could basically take this not and apply it to everything. So we could just say not A, and when you apply a not to this, it turns into the opposite. And sorry for the V, but that's just for time. And then not to C and hey. And if you look back, you're saying, hey, you, so we got to smooth that guy back out. And we're actually just going to get this. We're gonna get
If this is
guy.
on the test, you can't assume that you can just do it for all three at once, by the way. You actually need to show that you need to show it for two at a time and then show that that works. Because otherwise they say you're assuming something. Even though we know with De Morgans it does work.
Gotcha. So we would break this up one by one.
Yeah. So you would say not A or not B, and then you still have and C, but that's still being knotted. So basically you would need to briefly turn two terms into one to make that okay. But if that makes any sense.
That does make sense, I believe.
Okay.
So basically you're thinking of like this, like you're thinking of it as one. And you're thinking of this as, say, basically you're moving this here. I can't type this out. In my mind it makes sense. So basically you're thinking of it as this is your new A and this is your B. Is that what you're saying? And then you're nodding that? And probably told me what.
Yes, except the not A needs to be ORed with not B.
You could just, if you press control on my screen, you could type it out.
True. I could just annotate as well.
You could do that too.
So oh my, I have my keyboard disconnected.
Oh, you're good.
So no, I have a laptop so I can still type, but so assuming the original thing of the not A and B and C, you can then get not Um, here. You won't be able to see it for a second, but I am typing. Um,
Oops.
and we. How should I do or? Just with a V?
Yeah, go for it.
Okay. Okay, so like that. So you're grouping the A and B, so we don't care what it is momentarily. And we can do this by the law of associativity, where we can just say, hey, parentheses. So by we're considering A and B to be one thing. Well, we could call it D if we wanted. So then we're just doing De Morgan's law of D and C. You guys can see the text, right?
Absolutely.
Right.
Yes.
Okay.
And that looks a lot cooler than
Yeah.
That makes a lot more sense. Cool.
And
Thank
so
you.
then you can independently do the first part of the not A and B, and you would need to show this on on the test if there's anything like this.
Gotcha. I will keep that 100% noted. And I can't copy and paste that sentence, but there it is for all the words. Actually, I just copied it. That's super important, and that is a totally important thing to know. And that's law of associativity, correct? What's
The first step is laws of associativity, where I grouped the parentheses to just have A and B.
Beautiful.
And then it's just taking De Morgan's law.
Gotcha. All right, and then I'm just gonna send out this quick survey really quick because I want to ask people if they want to continue, if they want, like, because I know some people might have to go because it's approaching 1:30, but I'm asking if they want to like finish all the homeworks in the session and just have it recorded for them to get to later, or man, how do I ask a poll? This one, launch. Okay, cool. So I'm just asking some people if they want to keep going, because I know some people have to get going. And if so, I'll stay with whoever would like to stay and finish it up. Sorry this took so long, everybody. I hope this is useful to you, though.
Yeah, absolutely. This has cleared up a lot of different questions I've had.
Just waiting, just taking a little shimmy sham break. All the responses are in. Okay. Okay. So it looks like a majority of people just want to see it hammered out. So people who can't stay, you're always free to go. And this will always be recorded. And I'm just going to finish out the rest of this, and it'll be available for people to watch. You can feel free to stick around. But this does kind of end the official session. And I appreciate everyone who came here. And for people to stick around, I am still appreciating you. So, feel free to go if you have to go. Thank you for your time. I appreciate you, and I hope you have an amazing day, and good luck on your midterm.
I'm going to head out. Thank you so much. This is actually very helpful.
Of course, yeah.
Thank you. So good luck
have a
tomorrow,
good one.
guys.
Thank you, you too. All right. That is cool. All right, so we're gonna keep going, just because everybody was saying yes, or a lot of people, um, and yeah, this is democracy. Sadly, well, not sadly. We don't
Sadly.
we don't want a dictatorship. Although my girlfriend sometimes says that would be great, and she would like to be the ruler, but that scares me. The world that happens scares me. Anyway, jokes aside, what are we doing? So 2.1, did we finish? What number are we on? I'm sorry, guys. What number was this? Does anyone know?
19, I believe.
19. Thank you very much. So 19, homework 5, 2.1. 41 is the next one. And so.
So really briefly, how is this showing that each side is a subset of each other?
I didn't finish. Okay, yes, I got distracted. I'm sorry. Yes, so we proved that this is, okay, so we proved that this is, thank you, Ian. I appreciate that. That helped me remain focused. Okay, so we proved that this is this because we're able to break it down. And now we have to do it the other way. So now, if we have a, goodness gracious. Now we have to do this guy and break it down to this guy. And so we're going to take this guy, and that'll prove that this is a subset of this, because we've already proved that this is a subset of this by breaking it down into the equivalents.
All right.
Yes.
So are you missing quantifiers then? So shouldn't you say if X is an element of not A and B and C or whatever for each step? Because wouldn't that be what it is? So you're
Right.
showing that it's a subset by saying if X is an element of this thing, then it's an element of this thing, and that's the
Yes.
definition of a subset.
Yes, I am skipping some steps. Absolutely. You're right. So,
Okay.
yeah, you would say X. And once again, sorry guys, I got a little distracted just because I'm tired. There it is. Okay. Okay, going back, focusing, staying focused. We're saying this guy, we're saying X exists within that guy, and then we're breaking that down, basically breaking it down. Obviously, this would go deeper and deeper, and this guy, and that guy, and then we could say, since X is existing, within this statement, also exists within this statement. Then we could say that guy. Does that sound good to everyone? Or better, at least a little better.
Yeah, that looks cool.
Yeah.
Okay, coolio. Awesome. So I hope that makes sense. I can release these too. I mean, it's kind of sloppy, but if you want it, I have it. So we're going to do the same thing, but we're going to take this, and this is actually a lot shorter because it's just kind of the same thing but backwards. So if you look at this, you can just say, and once again, you'll probably have to combine them, I assume. You would have to combine some elements and say this, for example. Let's see. And of course, this would be in there as well. Then you could use what Aiden was talking about and just use the Morgans on these two, because technically these are two elements then. And you can break them up eventually to say this guy, which is going to be A. And of course, we want to break up this into the pointy guy. Okay, and then that is broken up like that. And then we have this guy, which we use the Morgans. No, So we have this law. Sure. That's fine. And we're just saying, hey, we're converting this to A because we're just doing the inverse, and we're converting this to a pointy guy, and we're just doing the inverse, and we're just doing a pointy guy, and we're just doing the inverse. And so we have that, but keep in mind that this whole thing is going to be knotted because we're doing De Morgan. So basically what we're saying is that this is equivalent to this because we could take the knot, put it outside of all this. You could think of it as taking out, factoring out a 2 or factoring out a knot in this case. And when you do that, you're just changing all of these guys to their proper form so that when the knot is thrown in, obviously you'd have to break this up like Aiden was saying before. But if you kind of think in like broader terms, this would just go in there and then you would have your equation. And from there, I think you would have to, you could basically do this again. And I accidentally did not combine them. I just like factored it out and said this, but Aiden's correct in that you want to combine them first. So I think that's a very good thing to mention, and that's why I'm making a big point of throwing it in there. And so then you have that, which means that since x exists within equation 2 and exists within equation 1 and vice versa, then they are equal. You can also prove that with a table. I won't go into the table. Well, would you guys like to go into the table? I guess that's more of a you guys question.
I think the table makes more sense just by putting it in logically, so I don't think we need to really cover it.
Okay.
Unless
Yeah,
somebody
but
else wants it covered.
absolutely. Just let us know. But basically, you just turn them pointy, and you just do what you would normally do. In that the union is, or sorry, the intersection. I'm gonna mess that up. The intersection, it even looks like an N. Intersection is and that means that they both have to exist, and that's a 1. And then the union, which is a U, is the OR, and that means that only 1 has to be a 1 to be 1. Anyway, limiting the confusion. Hopefully, I'm going to move on to 43, and this is not what I remember it being. Wait a second. 2.2.
All right, well, I've got to take off, but thanks, Gabe, for setting this up.
Yeah, no problem,
It
Eric.
really cleared up a lot.
Yeah, have a good
So
day.
good
Good luck
guys.
on your lab. See you around.
Thanks. See ya.
So I'm just going to cover 2.2. So 2.2 is here, and we have 17, which we already did. Cool. And then we have 19, which we just did, I believe. Yes. And then we have 31, which is this guy. Okay. This guy. There we go. And this is the second to last homework, by the way. So after this one, we have homework 6, and then we are done, I think. Unless anybody wants to go over anything else. So here we have the other homework and the other problem. And with this guy, you could kind of logic it out. I usually like to use doodles, but of course, you're always free to kind of think of it in a different way. So A union B is A. So that means that A or B is A. So if you think about that, if you have this, no, I'd rather use the logic because he's gonna use the logic on that. So, okay. oops, there we go. So if X is in A, then X is also in B. No, sorry. Oh man. Okay. So A union B. I think that would be the answer though. Just to double check. It might be the other way around. But A union B basically means that B has to have all the elements of A. So it's actually backwards. And that would mean that B is a subset of A. And so I know I kind of messed that up there, but let me make that better. And so basically we're saying, hey, we need to have B, and remember we're just thinking of this as or, so that it's equal to A. So that means that B can be in A, and that way, when you have an element in B, then it's also in A, and so this whole thing is fine because that's fine. But if it was the other way around, if it was B, and this was A, then if you had an or, well, it could be the case that there's an element here and it's not in A, and so that would not give you A. I don't know if I worded that well, and apologies if I did not. But let me move on to the next one, and let me try to break that down a little better. So here, I'm going to say A, or I'm not going to say anything, let me think about it first. So this is the intersection, and so with intersections, we're thinking of this, we're thinking of this, and we're thinking of the inside where they cross, and we can also think of that as a conjunction. And so with that, you want to say, basically, you want it so that elements are the same. So this is an A, and this is an A, and therefore that is an A, because they have to be the same. If they're not both an A, then it does not count. So it's a little different than the union rule. And so in this case, if you think of it, and you say, okay, well, let's do another subset thing, because I usually like to think in subsets. So we're thinking, I don't know, A, and then B, what would it be in A? Then we know the intersection of these guys. We know the intersection of this guy is this without kind of thinking about it, because that's where both of them have elements, and same with this guy. And we want all of them. Wait, didn't I just write the same thing? Excuse me, guys. Now I'm getting kind of pooped now that everybody left. Not everybody, but you know what I'm saying. But now that some people left, my exhaustion right now. So we have this, and so that's an intersection, and that's an intersection. So it covers everything, and so we know it's either going to be this guy or this guy. But we know it's going to be this guy, and so we're going to say B is a subset of A. Is that true? We're going to say A is a subset of B because A is in B on that right diagram. I'll just get rid of that other guy to clear any confusion. On that right diagram, we're saying A is in B, and the intersection, they both have the same elements in that little solid little circle in there, which is all of A. And so that's why I'm saying that. So moving on, we are going to say this one. So A minus B is equal to, this is also good for the test, A minus B is equal to A intersection not B. And so that kind of helps us because we know it's going to equal A. And so we know, basically looking at this guy, that we're talking about intersection. So we're talking about two circles that are going to be meeting up, and they need to share the same elements. So we know that not B must share the exact same elements as A in order for this to be true. So kind of thinking about that. Let's say, I believe we're going to have a subset thing going on. I'm not entirely, well, no. Actually, let's say it breaks up. And let's say if this is B and this is A, Yes, that's what I want to do. Let's go with that.
Your subset idea would work.
The subset idea would work? Okay.
Yeah, where you could say that it's the exact same as question B. You say A is a subset of not B by the same logic we used there. And so if it's a subset of not B, then we can say it's completely independent of B.
Oh, okay. So B, A is a subset. Yes. Thank you. Thank you very much. I appreciate that. Of not B. Yes, and so that's what he's saying, because he's saying the intersection will cover all of A, and so then you're good. And so in this case, I think this is the same as, or this would work.
Yeah,
I think
it's the
same
exact
thing.
thing. Same thing. Yeah.
And so you'd say B, the opposite would be everything in here, right? All of this, everything in the white square, and so the intersection of that would be all of A, and so that's kind of the same thing. And so you're saying, I think either would work. I think you could say not B is subset A, meaning A is sorry, A and B don't intersect.
I think they want you to use the term are disjoint
Are disjoint. Are
because
disjoint.
that means that the intersection equals the empty set.
Okay.
So
And so math-wise, I think, because I did mine, I didn't actually always type here, but I do want to kind of see what I wrote as well. Well, I will leave that alone. But B is a subset of A, not B is a subset of A. And I believe
opposite. A is a subset of not B.
A is a subset of not B. And yes, sorry. So now this is, goodness gracious, guys. My apologies. Just want to make sure this all looks good. And if people are saying this is a little too confusing, let me know, and I'll try to make it sound better. And so, yeah, if A is a subset, perhaps a different color will get me more awake mood. There we go. If A is a subset of not B, then A and B are disjoint. So there's nothing in there because A and not A does not exist. So what we're doing basically, this is a law, there we go. Now my brain's working. This is a law, and this is basically saying A intersect with not A does not exist. And since we just said that A is a subset of not B, we could say that this is basically, we could say the opposite too. We could say that B, and let me know if this is wrong, but B is also a subset of not A. And so then we can kind of plug and chug. And so what I did here was I just turned B into not A and vice versa. And that's why you can say that that's why this is the conclusion. Might be more confusing, might not be. I hope it's a little less confusing, but I'm going to move on to the next one. And if somebody wants to go back on that one, I can explain it a little better. This one, easy peasy. This is just a law. This is the commutative question law. It's a type of law. It's
Commutative. And the easiest approach to these might be, hey, come up with a hypothesis and then validate it with pictures.
yeah, I definitely go the picture approach on this because that helps me a lot. And then this guy would be intersection not be. Oops. Is That's basically what that one translates to, because this is just the rule there. And you can basically go, hey, once again, pictures. Actually, I think I understand this one if I write it out better. So you could say there exists an X that is both in A and not in B. Well, that's the first one, right? This is the first thing on the left side. On the right side, which is on the right side, we can say there exists an X that is both in B and not A. I'm sorry, this is not B. And so if you say, I don't know, X is in A or B or either one, then one is true, but not the other one. So, for example, if you could say, hey, that works, but then if you say X is in B, well, that doesn't work. So that means that A, not B, that A intersection I believe, or not intersection, excuse me. I believe that this is null in the case of this, because that can't happen. And so then you could say, because of that, you could say A equals B. That may be incorrect. Let me really quick pull up my homework because I 100% remember talking about that for sure. That is homework 5. And also, if somebody else like has a different way of thinking about that, just let me know, and we can hammer that out as well. But this is going to be 31, and perfect. It's right here. Yes, and so I said, yes, I said if X is an A, right? If X is an A, then it is true that this is true. X is an A, but this can't happen. And if X is in B, or if X is in not A, then this is true, but then that can't happen. So this means that A minus B equals B minus A because they are both equal to null in this case because they can't happen, which could be reorganized to A equals B. So basically, you could think of it as you could also think of it as being a subset. So the only way that these can be true is if they're null, if it's literally the null space. So if it's the null space, then yes, because if X is in A, then X is technically in everything, right? Because it's the null space. There's nothing there. X can't really be in anything. It's just null. And so since these are equal, that would be A equals B because it's in the null space. I think if once again, if somebody wants to word that a little better, let me know. But I will highlight this and just kind of be like, hey, that's a thing you should be wary for, because I might have not explained that too well, but I completely recognize that. Moving on to the next question.
Are we skipping D?
Oh, was there D? Sorry. D. Did we do D? We did not do D. No, we did D. That's commutative, right? This guy?
Well, it wants us to say something about A and B, no?
I think the back of the book on that one just said it was always true.
Does it just say commutative one?
Yeah, it says, I think it says
At the back.
always true.
I mean, hey,
Something.
that's a fair thing to say, I guess.
Let me pull it up.
I mean, that sounds right. That's what I would say. I just don't know if it wants any additional explanation.
Yeah, absolutely. I totally understand. Let me check it out. 2.2, number 19. No, not number 19, number 31. It says nothing, comma, because this is always true.
Okay, cool.
Yes. Okay. So moving on from that one, let me know if anybody has any questions, but I know I kind of butchered this one a little bit. And you'll have to excuse me for that. But you can always come back to that if you like. And we are leaving homework 5. So now we're in homework 6, which was the homework that our quiz was on. And I'm going to go and do that, which was 2.3. Yes, 2.3. And for this one, so we're just doing 3 questions. I said 5. Find the domain and range of each function. Okay, I'm going to take 2 of these, and we're just going to go with that. So we're finding the domain and the range, and how I like to think of this is you have an x, and that's basically leading to some y, and that's your range. You know, kind of like a graph. And so in this case, we'll do this one. So in this case, the function that assigns to each bit. Okay, so we're going to put down bits. Goes to 0, 1. The number of ones, which in this case is 2, minus the number of zeros, which is 1. Okay, so that's a number. So these are binary. These are just, that's an equation. It does that for, dot, dot, dot. And we're going for however many number of bits we got. So that's the domain. This is the range. And so the domain here is just, it looks like bits. So I'm going to put, and how the book says it, and the answers is the number of bits in the system. And then
The
the range,
domain is actually the set of bit strings.
the set of bit strings. Sorry about
Yeah.
that. Set of bit strings. Thank you.
The way to think about these is they're like, think about them like coding ways. Actually, it'll make it easier. Because you have your function, you have what you're passing in. What you're passing in is going to be your domain. That's your parameter. And so your domain is always going to be a set.
That's what I call.
And then the range is what you're returning. Range is also always a set.
Makes sense to me. Makes more sense to me now. So thank you. So yes, the set of bit strings in the system. Thank you, Aiden. And the set of integers, 100% agree. And then we'll do the this one. The function that assigns to each positive integer the largest perfect square. Okay. So I'm thinking 1, 2, 3, etc. I'll just put that down. And then this would be 1. The largest perfect square would still be 1. Just for fun, I'm going to do 6. And that would be 4, because that's the largest perfect square. So it looks like the domain in this case is the set of positive integers, which is kind of what they told us is going on. And then the range in this case, well, we only have basically perfect squares. Positive, well, I think perfect squares are always positive. Perfect squares are the set of perfect squares. 1, 4, 16, 64, other stuff. I would say that is solid, and let me know if it's not. And then we will move on, and we will say 15. So yes.
You might want to say you might want to specify that like it can't be 0 because 0 is a perfect square.
Oh, for sure. Set of squares. Yes, absolutely. Above 0. Thank you, Abe.
Cool.
Very cool. Okay, we'll just do, this was on the quiz, so I will cover the ones that were on the quiz, and I think that was this one. Easy peasy to copy, but maybe not easy peasy to, but easy peasy to copy, certainly. And then I believe there's this one. But maybe it's not easy peasy to copy. Okay, so we're talking about z, and z is all integers, which are basically, I think, of whole numbers, and they can be positive or negative, and that is our range. So this is our domain, this is our range, I believe, and so range is all integers, plus and minus. And so this is more my field, I think, a little bit better. And so we're going to say, hey, absolute value that can only cover the positive. So it is not onto. And let me just clarify what onto is. Onto means that the entire range is covered. And then 1 to 1 means that inputs do not have the same results. So in this case, D is also not 1 to 1 because you could plug in -1 and still get the result of 1. So in this case, also not 1 to 1 because this guy equals this guy. All right, this guy, m minus n, any combination works. You could have negative, you could have positive whole numbers. So I would say, yeah, totally. Yes, this is onto because it covers all integers, plus and minus. And then I would also say, I would say yes, 1 to 1. I want to say yes. No, I would say not 1 to 1 because you can have something like this. Because you could have 2 minus 2 equals 0, and you could also have 3 minus 3 equals 0. So you can't have 1 to 1 in that case. But you can have onto because it does cover everything. And that kind of, well, I feel like including both is important just to further down that detail. And so this one you cannot, because this is a positive number plus a positive number. So no, only positive integers can be made. So not onto. Not 1 to 1 either, because -2 is going to equal to 4. If you plug in -2 is going to equal, well, actually, not equal, excuse me. And then 2 and 2 is also going to equal 8. So cool. So moving on to the next question, 41. This guy. Yes, this is an important one. So show that they are invertible, and so if we got a bijection, then invertible, and that means both 1 to 1 and on 2. I don't know why I said that back. Goodness gracious. 1, 2, 1, and on 2. Okay, so to prove that something is 1 to 1 mathematically, we can say, hey, x1. Are we gonna name it? We need to name it like. No, wait, no. Let's just stick to x1. I don't think I have the mental capacity to come up with a cooler variable. So then we can also say x2, some x2, and so we can put those equal to each other. And basically, the b's will cancel out, and the a's will cancel out because they can't be 0, so they can cancel out because they're just a number and they're constants. And so x1 equals x2 basically means that any input you put in is going to get a complete, unique, random, different number. So like 1 will be, or 2 will be 3, and 3, 4 will be 5. You know, so that's basically what that means, is that you're going to get unique stuff. So that proves that it's 1 to 1, because each input is a unique output. I'll write that down. Each input, and if f of a equals f of b, then a equals b. Yes. And that's exactly, and this is injectivity, sorry. And injectivity is also 1 to 1. Each, thank you, both are injectivity. Or whoever did that, I don't know if it was, it might have been Nathan or Kiara. And sorry if I mispronounced your name, Kiara. Cool name though. Anyway, now we're going to prove on 2. And so to prove on 2, you just take the inverse. And to take the inverse, all you got to do is make this a y and leave that as it is, and then translate it. So when you translate it, you basically are going to get x is equal to y minus b, and then you have to divide it all by a. And so that is going to be your f of y, which is your inverse function. And so to prove on 2, you just do the same thing. You plug in y1, you plug in y2, and you notice that the a's are going to cancel out, because you just multiply it all by a, and you notice that the b's are going to cancel out. And so then in the range, you're going to get unique results too. So proves on 2. And so then we already proved the inverse, and all is good. So that's that one. And I'm going to move over to 2.4, unless somebody has a question on one of the ones that we've done, or if they want to do a different one, that's fine too.
Well, I need to go now. Thank you so much for this.
Yeah, no problem, Nathan. I hope you have a good rest of your day.
You too. Thank you.
I'll just finish this. I'll make sure to stay even if there's no one here, just because the polls wanted me to. But I may have to get a drink of water soon because I'm dying. So 2.4, 11C is what I have written down. And yes, okay. Mostly this was just kind of like a talking thing, not a proving thing, which is kind of good. And so it says let A of this. So this was on the quiz. And basically all you got to do is input 0, input 1, input 2 to find that. And so that totally works. And then you could also show that by plugging and chugging. So once again, once you have A, and sorry if this is a little hard to see for everybody. Oh no, I hope that didn't take me somewhere. I don't want to be. Oh no, it did. Oh man, sorry guys. All right. Anyway, I'm gonna try to explain once I get back to it. 2.4. 2.4. So 2.4 number 1. Okay. So then you just plug and chug. basically, and that will all work out. That will prove that A2 is in fact the A2 you calculated in part A. And then for part C, I just wanted to explain that really quick, is that to show that you want to basically use this equation that they give you and also this equation, and you want to say, hey, A of, well, I didn't say I was going to type anything, but now I feel like I have to. We're going to do that, and we're going to do that. And so you want to say this, you want to say -1, -2, and you have n -1 and 2, and we got the 2 there, so it's all good. And then what you want to do is you just want to plug those in. So basically what you have here is you're just going to plug this in here, and you're going to plug this in here. And I'm not going to do the complete math on this one because it is I am terrible at algebra, which surprises myself on a constant basis. But anyway, you throw that in there, and you're going to basically multiply all of that out. And when that's going to give you, when you multiply all that out, and of course, if you really want me to, I will, of course, but it would give you this. Sorry, the exponent thing is really throwing me off. Goodness gracious, it would give you the top thing, which is gone. It would give you this. It would give you that. So basically what we're doing is, so after you multiply all this out, just clarifying one more time, gives you this. And that's because you throw in n-1 for that, you throw in n-2 for that, using this equation. Throwing it in there gives you back an, so that proves it. And I hope that makes sense. If not, let me know. But anyway, moving on from that one, that was more of a short topic that I wanted to talk about. That got a little too longer than I expected. This one, I'm gonna do just B, because I feel like B gets to the point. So for B, and I can't copy. Oh, ooh, maybe no. I'm just gonna zoom in, and hopefully you can see that. Well, okay. So for this part, you basically want to handle the very rightmost, I don't know if you can see my mouse, but the very rightmost thing first. So we're talking about J, so we're going to manipulate J. So in this case, we're going to go through iterations, and we're going to say 2i plus 3 of 0, because it's starting at 0, which is 3 times 0, and then plus 2i plus 3 times 1, and then plus 2i plus 3 times 2 plus 2i, oh my gosh, plus 9. And so just to reduce this, I'm going to say that's 6, and I'm going to say that's 3, and I'm going to say that is 0. I understand why Adam was having trouble the other review session when he was trying to type all these out now. Okay, and then this is 8, and this is, let's see, 3, 6, 9. I think that's 16, I want to say. Let's see, 9, and that'd be 15, 16, 17, 18, maybe 18. And then you want to handle the second one. So the second thing is going from 0 to 2, and we're just manipulating I. So we're saying, and we're starting at 0 still. So 0 plus 18, because I just multiplied beforehand, and then 8, so just multiplying that 8 by 1 by 18, and then plus 8 times 2 is 16 plus 18, and then you'll get your answer of number. But I can't really do that right now in my head for some reason. But that's what you would do for that one. So that's your thought process that you kind of want to handle for these guys. If it's just one, I'm going to do the C one real quick. If it's just one, you still are going to do that a couple times. So for the C, you see that it's repeating 2 times. Even though J is not there, you're still doing that. So it's still going to be I plus I plus I. And then, oh my goodness, sorry guys. And then you're still going to repeat that the 3 times, but starting on 1, because you gotta make sure where you're starting. But I guess in this case it doesn't matter. But in future cases it might. So then you just kind of plug and chug, and that will also give you a manual movement, and everything is good.
Why are we using I for C?
I for C for this guy.
Oh, I was looking at 34. My bad.
Oh, gotcha.
I was like, hey, wait a minute.
No, you're good. But yeah, that would have confused me too. Sorry. We could do that one if you want. So for
No, it's the exact same thing. Just
backwards,
twice
right?
instead of. Huh?
Because you're working with J first, I think. So it would be like, would it be 1 plus or 0 plus 1 plus 2, which is 3, and then you want to do 3 plus 3 plus 3. I think.
Yeah, that would be what it would be.
Which would be 9. Cool. And then cool. I'm glad we covered that one though, because if that would have been on the exam, I would have freaked out a little bit. Of course we would have got it in the end because optimism and stuff, but always good to handle that. So now I'm going to move on to 2.5, and I just have 2 questions on that one. So I was about countability, very important topic. So in countability, and this is also on the resource sheet, there are 3 types essentially. I mean, there's probably more, but I think of it as finite, infinite, excuse me, I don't know why I said it like that, and then uncountable. And of course, in this, there's 2 subsets. There's countably infinite is usually what we are talking about when we say infinite. So I say 2.511, which was give an example of 2 uncountable sets A and B such that do. Very good question. Okay, I'm going to do the whole thing. Okay, so we know that in between, and let me further explain this, uncountable. So I like to think of it, and this might be wrong, but I like to think of it as forming an equation. So for finite, you know the start and end, such as 1, 2, 100. And I don't want to do. And then countably infinite, you cannot count the start to the end, but you certainly can make an equation about it. So if you say 1 and then 2 and then 3 and then blah, 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 to infinity, then you could say n equals n plus 1. Or yes, I think so. You're just making an equation. If you can make an equation out of it, then you're solid. But usually for real numbers, often, not always, they are uncountable, because let's say you have 1 to 2. Well, then you have 1.1 and then 1.01 and then 1.11, and then that could go on really forever. And you can't really form an equation, or it would be very difficult. Can't easily form an equation or predict, a pattern. And so it's uncountable. You can't really count it even theoretically. And so in this case, they want us to have two uncountable sets. So we already know, we're just going to use our real number example. We're going to use 1 and 2. We're going to do this for the whole thing, by the way. Maybe if I can think about the whole thing already. We're not going to do the whole thing. We're going to do this. We're going to do two different things each time. So we're going to do, these are real numbers in between 4 and real numbers in between 1 and 2 and 3 and 4. Union with, we'll say union with, because the first one is asking for finite. Well, let's just say 0. Let's just say 0. 0. Of course, you would want the set of 0. And so here you could say A intersection B. You can say A intersection B is just going to be 0. So then we're solid. That is still a, you can't really count these guys, but you can totally count 0. And so we're going to do the same thing so that it's finite. And then we're going to do the same thing and we want countably infinite. And so we're just going to say all integers. And that is basically all whole numbers, so like 1 and 2 and 3 and etc. And of course that also counts as negative, so negative 99. But that also could go on forever. Hopefully I worded that right. But that's kind of what I'm thinking, because those are totally countably infinite. And so, once again, A union B is going to be countably infinite because it is just Z. So in this case, it's a little bit cheating the system because you're just using, I mean, you don't really even have to think about messing around with the real numbers, but it's not illegal. So, you know, it's like jaywalking. I mean, they say it's illegal, but sometimes it's not. So uncountable. We will just change this to be 100. And so real numbers not unique with anything. And so we know that the intersection will be all the real numbers in between 3 and 4. And that is infinitely, that is just infinite. Well, it might be infinite. It's just uncountable. It's uncountable. It goes on. And you can't really make a pattern, and we're solid. So that's that one. And now 19. And ABC. Okay, so this one gave me some grief, so I thought I would share it. And I think the office hours I take for this one, although I don't remember 100%. Show that this are sets with this and this. Okay, so that basically means that when this is happening, when the cardinalities are equal, then they are onto and 1 to 1. Which is kind of going back to our function thing. I believe. Let me double check that before I don't lead you down the wrong path. So I know I took a lot of notes on that one. And that's it. That can only happen if and only if they are a 1-to-1 correspondence. This is the same, meaning this is the same for B and C, meaning they are both 1-to-1 and onto. Yes. So 1-to-1 correspondence. So meaning 1-to-1 correspondence. Same thing. Which I think Carl, he's a pretty cool dude. I don't know him too well, but I met him once. He's a nice guy. Carl in our class was talking about that in the chat the other day. And let's see. Okay, so then same for C and D. So then 1-to-1 and onto. And this is the cardinality. This is not absolute value, it's cardinality. So that's just the number of elements, basically, is that what we're thinking about. Not what is in there, but just the number of elements. So like you could think of like the finite thing again. You could think of, right, so this would be 99 elements. Or you could say also, or negative 100 to negative 1. So that would also be 100 elements. So they would have the same cardinality, but they have different values inside them. So I hope that makes sense. And so they're 1-to-1 and onto. And so I believe I'm gonna actually just quote what I said here because I don't know if I could speak for much longer without water. And so basically, you can say that A and B, so you could say this is a function f. And as we said before, we know that this is onto. And the function f is 1-to-1 correspondence, which means onto and 1-to-1. And C and D is H, let's say. And so that means, and I'll just quote this guy, that there is, if we make a function of this, then we know that we have this going on. And let me know if this is not making sense, because I totally get that this is kind of crazy looking. But we're going to work backwards, and I'm going to try to explain this the best I can. So ignoring this and just focusing on this right side, we could say f of A is going to be B, which is exactly what is happening here. F of A is B. It's a 1-to-1 correspondence. It's onto, just focusing on those first two parameters. So then the second thing, G of C, same thing. Okay, so in this case, I also said this is G. So combined H. Okay, and so G of C is D, and so that's just a 1-to-1 and unique correspondence. And basically, I'm combining them so that A cross C, because we know that back to our sets, we know that we're basically foiling stuff over. Because if we have like A is 1 and 2, is 3, we have A cross B, which is 1, 3, and 2, 3. And so we have that. So that's all I'm doing. Is basically I'm doing the cross product like they recommended I do. And so I'm doing that, and I'm basically putting this in parentheses with a little comma, and I'm just saying, hey, this is that function that we already know, and this is this function that we already know, and we are set. Okay, so big O is our last topic. Yay. Big O, I was very, very confused on until I went to the professor's office hours a couple times, twice to be exact, and he totally helped me out on understanding it completely, because I did not understand how it could be like everything, because I thought it only had I thought that K, perhaps by explaining what I thought, I can explain what you should not think. So in a function, you will have a point where this is happening and this is happening. And so there will be a point. Oops. There will be a point K. This is actually what we diagrammed in the book, where the green function goes past the blue function forever. And after that point K, after K, green is always higher than blue. But there is a point where blue is a little higher than green for a little bit. But since this is happening, since green is always higher than blue after a certain point, you can say that blue is big O green. And so what that means is that green will overpower blue after some element, after X passes some element K. And what I thought that meant is that it has to specifically be that K, which is the intersection of those two elements. That is not correct. K can happen, the professor helped me up on this. K can happen here, K can happen here, because yes, it does happen absolutely at the intersection, but it also happens here, because past this element G, green is bigger. Past this element F, green is bigger. Past this element L, green is bigger. And so that is why, that is the power of big O in saying that K can really be infinite in a certain case of C, because you could choose anything after that intersection too, as well, to be K, as long as it's always greater than. You have to make sure that that's always the case. But that's totally fine. So you could also say when X is greater than G, or when X is greater than L, even though they don't intersect. So that's fine. And then for C, for the constant, that can be anything, because you could have let's use a dark green. You could have green to be smaller, like a smaller, and then eventually, let's say at L, it gets really high and then it goes. Well, that's still the same C. It's just with let's say it's times 4 or something. It's 4 times our light green. It's 4 times this guy. Well, that means that there's a C in which, in this case, it would be L. So L is greater than, but then let's say there's an element past that A. Well, yeah, that would work too. You could say C is 4. Sorry, that's kind of gross. And K is L or A, or let's say Z or Z. Actually, that's like spell out a word here. Sorry. And so you could say that. And so that's just kind of like, I just wanted to hammer that out first, just get that out of the way so people could write that down, or have that in the recording. Just if somebody's struggling with that, I thought that was really helpful. And so now I'm going to touch on the 3 questions that I have for 3.2. And that is going to be down here more. All right. Okay. Let's do, is this 3.2? 3.1, sorry. I as to whether big theta and big omega will be on there. Aiden also put, I didn't even notice that. I don't know how long that's been there for. So Aiden is putting down the actual formula, which you can find in the resources thing, and totally I agree with what he is saying. I don't know where exactly that function, I believe it's this one. No, it's big omega, excuse me. Wait, big L. No, I'm talking about big O, not big omega. Big omega is a little different. So this guy is the function that Aiden was talking about, and basically if it's approaching infinity, eventually this G, let's think of the light green as G, will overpass blue, which is F, at some time. And the absolute value is just basically a way of just, I believe that's, honestly, but I think that's just a way of being more than, because f of x is usually less than or equal to the absolute value of f of x. So that's just kind of a way of hardening that point in what they're trying to say for big O. I believe big omega is the opposite. So that's the lower bound, if you will. And theta is the inner bound. So just think of it the other way. So you could say that I believe, correct me if I'm wrong on this, but you could say that in our previous example, the light blue is actually big omega green, because over a certain point k, it will become less than our function. And so if we go up to big omega, this is what big omega is. And so once again, we're saying g. Hang on, just trying to think of what this says. Okay, so it says the set of real numbers, we say that f of x is big omega. So, right, so this is saying that f of x is becoming greater than or equal to some constant times g of x, and that's big omega. Whereas the first definition, I really want to show the definitions because I don't want to get that backwards with everybody. Here's the picture. Here's the nice picture. The picture that's a little bit. So they're saying some constant. So here it says f of x is less than c g of x for some constant x. And I believe the big omega was saying the other way around. It was saying that some constant g of x is less than f of x. So if we consider f of x to be here, then we could say that some constant times g of x is less than, and it'll be that way forever. And so in this case, this is not the case, because g of x, even g of x eventually, I think, will overpower over like a really, 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 really long time, over infinity, like Aiden was saying. But for this case, it would be the light blue, because the light blue will always go under eventually. And so that would be the light blue being big omega of the group. And so theta is in between. Theta is you could have a constant that times it, and it's always under. Like, let's say that there's somehow you could multiply a c times this blue function to make it greater over the green. But you could also do it like 0.0001 and make it less than for infinity. That's just a case where you could go both ways. That's big theta, at least my comprehension. And now that I've said all that, let's do. There are only 4 questions, so I'll do 2 of them, if that's fine with everybody. And I will do. Okay, I got scared because I didn't think this was 3.2. So 3.2, we'll do this one. And we'll do an ordering because he did an ordering in his. So we'll do an ordering for sure. And then we'll do a, I don't actually have I didn't write these ones out because I was kind of hoping there would be a little break to write that out. Let's see. We'll do 11. Yeah, we'll do 11, and we'll do 15, because those are the 2 rough and tough ones. So we'll do that. So 11 says, show that this and show that this. So show that and show that. And I know that's kind of messy. And so I'm just going to go ahead and put that there. And I'm just putting this out just so I can kind of absorb it for a second. So I'm being a little pooped. But there we go. So first we're going to show that this, and then we're going to show that this. And so looking at that, we can say, hey, 3x to the 4th plus 1. I don't know if you should do this, but kind of how I like to do it, and how they kind of did this in the book a little bit in the back of the book. They didn't go into too much detail like proving it, but I kind of like to say this. It's less than x to the 4th over 2, like in this case, when Well, in this case, if it's 1, then that's going to be 1/2, so that's not true. And if it's 2, that'll be 2 to the 4th divided by 2. Well, that's way bigger than 1. So when x is greater than 2, in this case. And you could do the other way too. You could also, I'll just do this first. So that means that 3x to the 4th, when x is greater than 2, plus 1, is less than 3x to the 4th. You could lessen it, as the professor said. You could just say x, and then you could go further and say x to the 4th. Because what our main goal here is we're going to get we want to get the same power. And so there you go. And then you could say, hey, that basically is equal to 4x to the 4th, which is going to equal basically 8, if you think of that, like 8x to the 4th over 2. Whoops. Because then you're going to multiply it by that 2, and it's going to reduce down to that 4. Of course, there are a bajillion ways, 100 million ways to prove this. But in the back of the book, I'm just using the back of the book example because it just seems like they would want us to do that first. C in this case would be 8 because we proved it that way. And K would be 2. And of course, we could do this a different way and say, we could say, hey, this is less than x to the 4th over 2, like this specific, this front one. When do I have the brain capacity for that? Yes. So when that's kind of jumping the gun. So how I would kind of think of it in that sense is you're solving the C first. But I don't know if that's what you want to do because the book recommends that you do the K version. But if you wanted to think of it this way, you could also say, hey, if C is 6, then you're basically saying 6 over 2, which is 3, x to the 4th. And so that's less than or equal to 3x to the 4th. So those are equal. So obviously this is not going to be less than. This is just going to be equals. So we got to go one step up. So you could say C equals 7. But also what the book did, once again, C equals 8. And so you could have that whole thing. But then you got to like solve that with the, I think you could say 8 x to the 4th over 2, which is 4 x to the 4th. That's just kind of reverse engineering it because then you kind of got to plug and chug and you got to think of, okay, 0, and then this is 0, and so that would be 1, so that doesn't work. And then 1, and then that would be 4, and this would be 4, and then 2, and then x is greater than 2. But I really prefer this way, just because it proves it while you're doing it, and that's pretty nice and good. This one is fairly, if that's a word, and that is that this is less than that. If you just kind of think of what we just did a couple of minutes ago about the plug and chug, you can kind of look at it and go, okay, well, when x, oops, this is true, when x is greater than 0, because, well, even really less than 0, but less than or equal to, sorry, I said greater, less than, no, greater than or equal to 0, excuse me. When x is greater than or equal to 0, this is true, because you plug in 0, then this is 1 on the right side, and this is 0 on the left side. And 0 is less than 1, so we're happy. And so we could say k equals 0, or you could say 1 or 2 or 3 or 4. But in this case, 0, because we proved 0. And we're going to say our c is 1, because that's just the actual function. And that's also what they have in the back of the book. And that's actually as far as they went for proving it, which I thought was, I mean, hopefully we can kind of send down the proof like that, but that's an existence proof, if you will. I believe. And so, moving on from that, I'm gonna hit up the last thing, which is I believe 21, and we're just gonna cover that. And if anyone has any more questions, we can go over them. If not, I may take a very long nap. Get some tea too. So I'm just going to go ahead and do this. Okay. Of course, the exponents are not always perfect. And for my brain, I'm going to, I don't like how that looks. I'm going to save this to the 1/2, or to the 0.5 actually. And Zynga, we are going to make a thing now. All of this knowledge. I don't know why it's doing that. Anyway, for the list, I have it in the resources page for you guys. And of course, you can always update that. But I have a constant basically is less than a log n. I honestly don't remember, which is why I printed it out. Yeah, give me 1 second for that, guys. Sorry. It should be on like the second to last page. Yes, it's on the second to last page exactly. That's kind of neat. Okay, so this is you always want to write this out when they ask you. I mean, if you don't know, which I don't know, so I'm always going to write this out. And instead of 2, we'll just put a. That's less than a to the n. Just think of a as some variable or number, and then you could say n. Okay, so knowing that, we're immediately going to look at this factorial, and that one is very great. So we know that that's going to be the highest one, and we're just going to go downwards from there, actually. So downwards, we have a to the n, and these were factorial. And so if we're looking at that, I believe those are the only two. Well, if you're looking at that, you go, okay, that one, and we know that just from kind of looking at it, that if we plug in 1 to n, then this one's going to be smaller. So we're going to put this one as smaller, and the next one is greater. So that's what we're doing. And now we're going down to the next smallest. And this is this guy. And so that's that right there. And I don't know if there's another one like that. I don't think so. And so I think we're good on that. Wait, this looks kind of similar. This one and this one look similar. I'm ignoring the, even though this kind of looks similar, this is going to be the next one down. So this guy looks similar with this guy. And it looks like that one is higher because if we just plug in, I mean, if we ignore the constant and if we think of a very, very long time, and if we think of the graph, you could kind of do that. You could think of the graph, or you could always, it's a calculator-based test, so you can always graph it. But, you know, I believe the square root looks like that. After a very long time, it will say that that divided by a million, excuse me, is going to be like after like a long time. I know that's kind of like blasphemy to put that because that implies there's more than infinity, but just theoretically here. So we're going to say this is going to be greater than I hope that makes sense. This guy. And
Since we're allowed to use a calculator, do you think we could use Desmos? It's technically a graphing calculator. It's just a lot easier to use.
maybe I would email him on that because I don't know, because he said you could use well, I don't know. He seemed I don't know. I'm not gonna speak for him, so I'm not sure. But I would email him on that to make sure. But I would just bring a physical one just to be sure. But that would be cool.
Yeah.
That would be super cool. Anywho, the last one was n log n, which is just you don't even have to think about that, which is good because I am running out of brain. And that's done. That's done. Those are done. This is done. This one. And so that's the last one. And that makes sense too, because that would be below that guy. So that's pretty solid. And that is our answer. And
Would-
so, yes.
Would square root of n go in the n, like at the beginning?
Square root of n. This guy?
Because like it says that square root of n before 1,000 log n.
And the answer?
Yeah, so I was wondering if it would go like in the beginning.
Ooh, good question. I might have messed that up.
And
let me
also,
see.
actually, n log n
Yes.
should be greater than n.
You're
to,
right.
0.5 as well.
You guys are absolutely right, because n log n is greater than n. Yes, I'm sorry, guys. Thank you very much for holding me up to that. I appreciate that. Because we want to be accurate. So yes, absolutely. So this, just moving things around. So this guy would be, I don't want to do this. This would be greater than those two guys, correct?
It should be less
Yeah.
than the n squared. Yeah.
Less than the n squared, right? And then, because we're talking about norm. Thank you for holding me up on that, Kara. I would not have caught that at this moment in time. And so that's solid. That's solid. And yes, that would be less than. And once again, I would use a graphing calculator to double check all that. And the reason why this is the case is because I can actually explain that a little better. Is because I mistook it for this, and I just said A was 0.5, but I didn't go ahead and think about that for a second, because if I thought about that, you could break that up into saying this is less than n, because for example, 2 or 4, 4 is, if you plug in 4, you get 2 is less than 4. And so since that's the case, that is here, and so that makes sense that this is less than that. So thank you very much. And then, what was the other thing? I messed up there. Sorry, guys. Putting me on the spot. Was there one more thing? I think there might have been. Let me check my homework and see what I put.
What base is the log supposed to be?
10, I believe. That's what I do, at least.
Its base is n?
I said 10.
Oh, 10. Okay.
Yeah, I just assumed 10.
Okay. Yeah,
then
because
I
if its base was n, I was gonna say like, hey, wait a minute.
Yeah.
That would just be 1.
Yeah. Okay, so I have that and that and that and that and this. Yes, that matches what I have for my homework. Yes. F2, F1. I wrote it as I wrote down the function, so I kind of have to look back and see what's going on. But yes, that is what I have. Super cool. Okay. That is, I wish there was, is there like a party emoji, perhaps? No. I'll just do another smile. Okay. That
So
is
actually,
all the
I did
home-
have
Yes,
I did have one question.
100%.
So I know that log n is going to be less than the n to the half, but what would the power of the n have to be to be less than log n? Do you know? Because I don't.
To be less than log.
Yeah.
Oh. Zero.
Would it have to be 0?
Well, if
Because
you
I feel
had
like n to the like 0.0001, would that still always be greater than log n in end behavior? Because that kind of just doesn't feel right.
you know, I think even if it was like, I mean I don't think that's going to be an example, but like that, I think that would still overpass. I think that's still greater than log n after a point. I really
Huh.
do. I really do. I can't prove it. Can't prove that. Maybe I'm wrong. Probably wrong. But that's what I think. You would have to graph that. And I am sorry that I can't answer that too well.
Okay. Then I guess graphing calculator all the way.
Graphing calculator all the way. Absolutely.
Okay.
Yeah. Thank you guys for coming. If you have any more questions, Kara, you stayed through the whole time. So if you have any questions that you just want to hammer out, you can always do
Oh
that.
no, that was all I had. Thank you.
Yeah, no problem. No problem. Good luck on the midterm, guys. You both are going to do awesome, I know for sure. And I just
You
wanted
too.
to put this up. Thank you. Thank you very much. And together we were able to kind of think about this stuff. I definitely made a few mistakes along the way, but thank you guys for giving your input and helping me out. And I'm going to end the recording and end the session. Actually, I'm going to end the recording right now.